What's going on, Bestie? This is your comprehensive, all-in-one, everything that you need to know for the ATI TEAS version 7 math portion of the exam. Let's get started. So let's start by taking a closer look at breaking down a numerator and denominator. So the numerator is the number that is above the fraction line and represents how many parts of a whole that you have. So here we have an example of 3/4. The top number 3 is our numerator. The denominator is the bottom number below the fraction line, and it represents how many equal parts of the whole are being divided. So in this particular case, our denominator would be 4. To make it easy, the denominator helps us understand the total parts that we're considering, while the numerator tells us how many of those parts that we're actually focusing on. To understand fractions better, let's visualize a pizza, often served in 8 uniform slices. To mathematically model this, we can represent the whole pizza as the number 1 and divide it into 8 equal parts, indicating the division of those parts. This means that each piece represents 1/8 of the entire pizza. If you consume 2 slices, that equates to 2/8. Now let's imagine a scenario where the pizza is sliced into quarters instead of 8s. In this arrangement, each piece accounts for 1/4 of the pizza. Interestingly, consuming 1/4 of a pizza is equivalent to eating 2/8 because these fractions represent the same quantity. If you divide the numerator and the denominator by 2, 2/8 would be equivalent to 1/4. This is a demonstration of equivalent fractions, illustrating that despite having different denominators, the fractions can express the same value once they are simplified. Now that we have a better understanding of fractions, let's focus on the concept of place values and understand their application when it comes to decimals. As a quick refresher, consider the number 1,234. It's a familiar territory where many of us recognize the rightmost digit before the decimal as being the ones place. The 4 stands firmly in the ones place, truly representing its face value. Moving 1 digit to the left, we find ourselves in the tens place, where each value is 10 times greater than the 1. The 3 in this place value represents 30 as it occupies the tens place. Progressing further to the left, another leap by 10 brings us to the hundreds place. And in this place, that digit is not just a 2, it also equals 200. And finishing out, moving further left brings us to the thousands place, making the 1 in this place actually 1,000. Now, as promised, we're going to deepen our exploration by introducing a decimal point to the right of the ones place. The decimal serves as a critical role for delineating where the ones place lies. So moving to the right of the decimal allows us to expand our numerical landscape indefinitely, accommodating as many decimal places as needed, each with its own significance. So let's consider this. When we're transitioning from the hundreds to the tens place, we're ultimately dividing by 10. Moving from the tens to the 1 place, we're also dividing by 10. So what name would we give the position immediately to the right of the decimal? What results from dividing 1 by 10? You end up with 1/10 or 1/10, leading us to understand this next position as the tens place. If we move 1 position further to the right from the tens place, what do we call this new position? It results from dividing a 10th by 10, effectively giving us 1/10 of a 10th, which leads us to identify this place as our hundredths place. Pushing even further to the right, we advance 1 more space. What designation does this position hold? Well, dividing a hundredth by 10 is considered as 1/10 of 100, bringing us to 1,000ths place. So in this example, instead of us having just the number 1,234, let's expand it to 1,234.567. What does these additional digits signify? Well, the digit 5 here doesn't simply stand for 5, it symbolizes 5/10. Moving on to digit 6, it embodies 6 hundredths. To make it crystal clear, 6 hundredths can also be represented by placing a 6 in the hundredths place, which is 2 positions to the right of the decimal. Lastly, what does 7 signify? It stands for 7 thousandths. To write this in decimal form, you would place the 7 in the thousandths place, which is 3 positions to the right of the decimal. So zooming out, the concept of place values allows us to extend indefinitely to the right of the decimal, enabling us to represent mathematical numbers with more precision. Next, let's talk about percentages. So percentages are common parts of everyday life. We encounter them in numerous situations, whether it's a 30% discount during a sale, leaving a 20% tip at a restaurant, or hearing that there's a 50% chance of rain in the forecast. Percentages are everywhere. But what exactly do they represent? The term percent derives from the Latin word centum, meaning 100. So essentially, percent translates to per 100 or out of 100. It serves as a method to express quantities by scaling a total of 100 and then describing a specific value as a portion of that 100. So for example, scoring 90% on the ATI TEAS exam implies that in terms of ratio, you have achieved a 90 out of 100. This could also mean 9 out of 10 questions correct, 18 out of 20, or even 450 out of 500, all reflecting the same proportionate relationship to 90%. To adjust larger numbers down to 100, we apply the same operation to corresponding smaller numbers. So for instance, to scale the denominator of 10 up to 100, we simply multiply that by 10. Similarly, we would multiply 9, the numerator, also by 10 as well. This would give us 90 over 100. Thus, percentages function as ratios, representing a particular type of ratio that benchmarks numbers against 100. While seemingly arbitrary, that benchmark of 100 provides a convenient standard for comparison, making it easier to understand and compare different quantities. Viewing percentages as basic fractions offers a clear perspective. For instance, 80% translates to 80 out of 100. As we've learned, simplifying fractions involves dividing the numerator and denominator by a common factor. Here, dividing each side of the fraction by 20, we arrive at 4 over 5, illustrating that 80% is equivalent to 4/5. Exploring another example, 50% is the same as 50 out of 100. Reducing the fraction by dividing both numbers by 50 yields 1/2. Logically aligning with the fact that 50% represents half of 100. For smaller percentages like 3% represented by 3 out of 100, further simplification is impossible, indicating that some percentages like 3% are already in their simplest fractional form. Converting between percentages, fractions, and decimals should be a pretty straightforward process when using this method. Let's test our understanding to ensure that we have fully grasped the concept. We've explored how fractions, decimals, and percentages can each represent the same numerical value, highlighting the flexibility of numerical representation. Now, how do we convert between them? I've included a memory trick that is actually found in my study guide to help you bridge this concept of converting between fractions, decimals, and percentages. So let's take a closer look at the conversions going either way. So if we start out with a fraction and we want to make it into a decimal, all we have to do is divide the numerator by the denominator. 3/4 would give us 0.75. Now, if we had to convert between a decimal to a percentage, we would simply multiply by 100 and move the decimal to the right 2 places. The same thing if we wanted to go the other way. If we wanted to go from a percentage to a decimal, we would simply divide by 100 and move that decimal place to the left 2 places. And if we had to take that decimal and convert it to a fraction, we would divide by the place value. We know that 0.3 is in our tenths place, so this would give us 3/10. Let's consider another example of 30%. Converting this into a fraction is pretty straightforward since we understand that percentages are based on 100. Thus, 30% translates to 30 out of 100. To simplify this fraction, both the numerator and the denominator can be divided by 10. Here's a quick trick though when you're taking your test. You can simply just remove the trailing zeros to help you get your answer when you have fractions that are like this. So 30 out of 10 is going to equal 3/10 in its simplest form. Now, to express this as a decimal, all we need to do is identify the tenths place. For 3/10, this means that we're going to place the 3 in the tenths position, resulting in 0.3. This demonstrates 3 distinct methods for expressing the same numerical value, showcasing the interchangeability between fractions, decimals, and percentages. So our first practice question states, convert the fraction 5/8 to a percentage. So we know that we are starting with the fraction 5/8 and we need to convert it to a percentage. So this is really simple. We're going to divide 5 by 8 and that's going to give us 0.625. Now, as we said before, we're going to multiply by 100 and move the decimal to the right 2 times. So we would go 1, 2. This would give us 62.5, leading us to believe that our correct answer is C, 62.5%. What is 0.2 expressed as a fraction? Simplify the fraction. So we know we're going to have to do a little extra math to come up with our answer. So we start with 0.2. We know that for certain as our decimal, and we need to convert to a fraction. In order to do that, we're going to divide by the place value. So as we learned in decimals, that number immediately to the right of the decimal place is our tenths place. So that means that we are going to convert 0.2 to 2/10. But again, we have to simplify our fraction. So in order to do so, we need to find the most common number that can be divided in our numerator and our denominator. That common number is going to be 2. So we're going to divide both sides of our fraction by 2, and that's going to give us 1/5. Do we have an answer that's 1/5? We do. The correct answer for this equation is going to be B, 1/5. Moving on to our last practice question for this section, we have convert the percentage 25% to a decimal. So we start off knowing that we have a percentage of 25% and we need to figure out the decimal. We do this by dividing by 100 or simply moving the decimal to the left 2 times. So in this, we know that our decimal would be behind the number 25 and we're going to move it to the left 2 times. This is going to give us 0.25. But you cannot have a decimal without having a whole number in front of it. So in this case, we want to add a 0. So it's going to equal 0.25. Do we have that answer? We absolutely do. The correct answer is going to be A. So let's start with order of operations. We all understand how to perform addition, subtraction, multiplication, division, and so on. Now it's time to explore scenarios where these operations are going to be combined and applied simultaneously. To establish protocol for executing multiple mathematical operations, we use the proper sequence known as PEMDAS. This acronym represents parentheses, exponents, multiplication, division, addition, and subtraction, guiding us through the sequence in which these operations should be carried out, moving from left to right. As we work our way through, initially we are going to address any calculations within parentheses. Next, we're going to handle exponents. And then after this, we're going to look at multiplication and division. Now, it's really important to understand that we are going to perform this by moving from left to right. Neither multiplication nor division takes precedence over the other. So if our first operation is division, we would perform that operation first. Finally, we conclude with addition and subtraction following those exact same rules. Neither addition nor subtraction are going to take precedence over the other. So if our first operation is subtraction on the left, we are going to perform that operation first. Let's take a look at an example of what this will look like on your TEAS. So our first equation is 4 plus our parentheses 3 times 2 minus 8 divided by 2. So the very first thing we want to do following PEMDAS is perform the operations within the parentheses. We do this by multiplying 3 times 2, which is going to give us 6. Next, we're going to move on to exponents. We don't have any, so we can automatically skip this step. Then we're going to perform multiplication and division. Remember, we're moving from left to right. So the only multiplication and division that I can see is the 8 divided by 2. We're going to perform that operation and it's going to give us 4. And then lastly, we're going to finish up with our addition and subtraction, again, moving left to right. Nothing takes precedence over anything else. So in this particular case, we have 4 plus 6. That's going to give us 10. We're going to drop down our minus 4, and that is going to give us 10 minus 4 is equal to 6. So the correct answer for this equation is going to be 6. Let's take a look at another example before we move on to our practice questions. So we have 15 plus, parentheses, 3 plus 2 raised to the power of 2 minus 9 times 6 plus 2 raised to the power of 3. So it looks a little complicated. Hang in there with me. We're going to get through this. So first, we're going to perform the operations with the parentheses first. So 3 plus 2 is the only operations we see within inside our parentheses, and that is going to give us 5. Moving down, next, we're going to calculate our exponents. That's our powers and our square roots. So we have two exponents here. We have 5 raised to the power of 2 and 2 raised to the power of 3. 5 raised to the power of 2 is going to give us 25, and 2 raised to the power of 3 is going to give us 8. Now we're going to perform our multiplication and division, moving from left to right. So as we can see here, we only have one multiplication, and that is 9 times 6. So 9 times 6 is going to give us 54, and that'll end that portion of PEMDAS. Lastly, we are going to add and subtract, again, moving left to right. Starting from the left, we have 15 plus 25. That's going to give us 40. 40 minus 54 is going to give us negative 14, and then we're going to add 8. And that is going to give us our correct answer of negative 6. Let's start with our first practice question. Calculate the following operations. We have 5 times, parentheses, 2 plus 3, minus 4 raised to the power of 2, plus 6. So we're going to start out with our PEMDAS with our parentheses. So in parentheses, we have 2 plus 3. That's going to give us 5. So our new equation is going to be 5 times 5 minus 4 raised to the power of 2 plus 6. Next, we're going to move down to our exponents. So we only have one exponent here, right? That's 4 raised to the power of 2. So our new equation is going to be 5 times 5 minus 16. That's our equation we just did, plus 6. Now we're going to move on to multiplication and division, again, moving from left to right. So if we take a look here, we only have one multiplication. That's 5 times 5. So that's going to give us 25 minus 16 plus 6. And in our last step, we are going to do addition and subtraction, again, moving left to right. So we have 5 minus 16 is going to give us 9. So we're going to drop down our plus 6 that we have left over up here. And 9 plus 6 is going to give us 15. So the correct answer for this equation is 15. And yes, there it is. Our correct answer is C. Next, let's delve into the concept of rational and irrational numbers. So at its core, a rational number is simply any number that can be expressed as a ratio of two integers and the denominator cannot be 0, right? It's right in the name, ratio, rational. It's going to be really hard for you to forget that when you're taking your TEAS. Let's take, for instance, the number 1. It can be depicted as 1 over 1, or negative 2 over negative 2, or even 500 over 500. These examples all demonstrate various ways to represent the number 1 as a ratio of two integers. And theoretically, there's an infinite amount of ways that you can do so long as the numerator and the denominator are the same. Similarly, the number negative 7 can also be expressed as negative 7 over 1, 7 over negative 1, or even negative 28 over 4. The list of representations when it comes to negative 7 is also endless. It's clear that negative 7 is a rational number because it fits the definition of being expressed as a ratio of two integers. So what about numbers that aren't whole integers? Consider, for example, the number 3.75. How can we express this as a ratio of two integers? One way we can do this is to look at 3.75 and convert it as a fraction. That would give us 375 over 100, which is the same thing as 750 over 200. Alternatively, we can understand that 3.75 is 3 3/4, which converted into an improper fraction would give us 15 over 4. So how do we do that? What we would do is we would multiply our 3 by our denominator of 4. That would give us 12. And then we're going to add our 3 that is in our numerator, giving us 15 over 4. What happens when we encounter repeating decimals? So consider one of the most well-known repeating decimals, 0.33333333, which continues indefinitely. We signify this repetition by adding and placing a bar over the number 3, indicating 0.3 is a repeating decimal. There are countless other examples of repeating decimals, but the key takeaway is that any decimal with a repeating sequence, no matter how long, can be represented as a fraction. This is going to hold true even with sequences with millions of digits that repeat endlessly. So you might be wondering at this point, hey, Nurse Cheung, with everything that we've covered so far, including integers, finite non-repeating decimals, and repeating decimals, what's left? Are there any numbers that don't fit into this category of rational numbers? Some of the most renowned numbers in the entire field of mathematics fall into this category, and we call them irrational numbers. These numbers cannot be expressed as a simple ratio or two integers. I've highlighted a section of significant examples that you're probably going to see on your TEAS. So take pi, for example. The ratio of a circle's circumference to its diameter is known as an irrational number. Its digits extend indefinitely without termination and without forming any repeating patterns. Similarly, E, which arises from concepts of continuously compounding interest and complex analysis, never ends or repeats itself, also making it an irrational number. The square root of 2 is also irrational. You might wonder if these examples are merely exceptions, or perhaps most numbers are rational, with only a few rare irrational cases that we're highlighting here. However, it's crucial to recognize that while these numbers might appear to be exotic due to their unique properties and applications, they are not as rare as you might think. Consider this perspective. I mentioned the square root of 2 as an example, but if you calculate the square root of any number that isn't a perfect square, you're going to find yourself with an irrational number. Moreover, when you combine any irrational number with a rational number, whether it's an addition or multiplication, it's going to result in some kind of irrational number. This demonstrates just how abundant irrational numbers actually are when we're looking at the mathematical landscape. Let's take a look at our first example. Which of the following numbers is irrational? So let's break each one of these down. So we have 8 divided by 2 is going to give us 4. We have the square root of 16 also gives us 4. So we can automatically eliminate A and B as being the correct answer because remember, we're looking for an irrational number. Next, we have the square root of 15. Oh, look at that. We have a very long number, right? We have 3.87298, so on and so forth. But let's finish out. We have 2.75. 2.75 is a rational number. So out of all of the options that we have available to us, C is going to be the most correct number because there's a lot of repeating decimals, but they don't follow a pattern. Our next question states, which expression results in an irrational number? So again, we're looking for irrational. So starting off with our handy dandy calculator, we have 25 divided by 5 is going to give us 5. So we know that that is rational. We can eliminate that. 2 raised to the power of 2 is 4. That's also, again, a rational number, so we can eliminate that. We have the square root of 49. The square root of 49 gives us 7. So again, we know that that is also rational. We can eliminate that. And our last number is the square root of 3. And again, look at that. We have a very long number. We've got 1.73250, so on and so forth. So out of all of the options that we have available to us, D is the most correct answer because remember, we have a non-terminating decimal with no repeating patterns. So when we see those kind of numbers, we know we have an irrational number. Now that we have a better understanding of rational and irrational numbers, let's discuss how we're going to order and compare rational numbers. We're going to sequence these 6 numbers from smallest to greatest, with the smallest number positioned all the way to the left of our number line and the largest number all the way to the right. I encourage you to pause this video and try to arrange them yourselves before we tackle it together. Let's proceed with how we're going to get the solution once you've given it a shot. We'll utilize a number line to assist us with this task, which I've prepared for your convenience. Let's begin by examining each number one at a time. So when it comes to your t's, the best option is to plot one option at a time and convert any fraction that you have to decimals to make it easier to compare on the number line. So let's examine this process. So we start with the number -3/4. So when we do our conversion, -3/4 is going to give us -0.75. So we're going to mark it on our graph right here. Next we have 0.5. 0.5 is going to be more on the right side of our number line. Next we have -1.5. Again, looking at our number line, it's going to be placed right in here. 2/3. So again, we're going to have to do a little math. 2 divided by 3 is going to give us 0.6. And again, we add our little bar on top of our 6 because it is an indefinite 6 number pattern. It's just 6, 6, 6, 6, 6, 6, 6, so on and so forth down the line. So 2/3 is going to be right about here on our number line. Next, we have -1/2. So -1/2 is going to give us -0.5. And we are going to put that right here on our number line. And then our last number is 1.75. So 1.75 is going to be way over here to the right of our number line. So if we're taking a look at this, we've already plotted it, we can get our numbers from least to greatest. So least is all the way over here on the left and greatest is all the way over here on the right. So we're just going to move our way down. So I have the answer down here for you already. So we have -1.5, -3/4, -1/2, 0.5, 2/3, and 1.75. That is the correct answer for least to greatest with this numerical data set. So we just learned about the number line method when it comes to ordering and comparing rational numbers, but there's a lot of people that also use the stacking method, so I did want to address it in this video. So the question is asking, order the following set of numbers from least to greatest. As we know, when we're looking at a number line, when it comes to the negatives, the farther away that we get from 0, the more negative it becomes, right? So what we do in this method is we're going to stack all the numbers vertically and line them up based on their decimals. So if you look here, all of the decimals are lined up so that we can compare our numbers. Now, the reason why this works so well is I want to draw your attention up here to the right of your screen. So if we're looking at a set of numbers that are lined up by their decimal points, it really helps us understand how each number is greater than or less than. So looking at our 2 examples, we have 5.347 and 5.582. So we have to figure out which one is greater, which one is least. So we start with the first number to the left of our decimal. So they're both 5. So we automatically, those are equal to each other. We can move on to the right. So our next set of numbers, we have 3 and we have 5. Well, is 3 greater than 5? No, absolutely not, right? So we can say that 5.82 is greater than 5.347. So it just helps kind of visualize a little bit better if this method works for you. So let's take a look back at our example here. So again, whenever I'm doing calculations with comparing and ordering rational numbers, I always want to start with our negative numbers. So I'm only going to focus on our -0.75 and our -1.5 and our -0.5. So let's take a look. So we start with our first numbers. We have 0, 1, and 0. So as we discussed, as we move further away from 0, the more negative the number becomes, and it also becomes the least. So based on this, we have -1.5. So we know that our first number, our least number out of this data set, is going to be -1.5. So next, we're going to move on to our next numbers. Because both zeros are equal, we can automatically eliminate those. So now we have 7 and we have 5 of our negative numbers. Again, the further we move away from the 0 on the negative side of our number line, the more least it becomes. So 7 is greater than 5, which means that 0.75 is going to be less than negative 0.5. So now we've moved through all of our negative numbers. We can automatically eliminate those. Now let's take a look at our positive numbers. So with our positive numbers, again, we're going to be looking at the first number. So we have 0, 0, and 1. So 1 is obviously greater. Remember, the further we move to the right of our number line, the more greater the number becomes. So we know that 1.75 is going to be our greatest number. Now we have to figure out which of these two remaining numbers are going to be greater than. So we have 5 and we have 6. Is 5 greater than 6? Absolutely not. So we can put 0.5 here and 0.6 here. So out of our data set, this is going to be our least to greatest. All right, our practice question states, arrange the following rational numbers from least to greatest. So as we know, based on our number line, as we move further to the left, it becomes more least. As we move further to the right, it becomes more great. So let's take a look at each individual number. So our first number we have is negative 3/4. So we know negative 3/4 is equal to negative 0.75. So we can automatically put that right about here. And I always just write the number on top so that way I know. Let's take a look at our next number. We have 0.5. We can go ahead and put that there. We've got negative 1.25. So negative 1.25. Next we have 2/3. So as we know, 2 divided by 3 is equal to 0.6 with a bar above it because, again, it goes indefinitely to 6 in the same pattern. So 0.6 is just going to be a smidgy over here to the right of our 0.5. We'll put 2 over 3. And then lastly, we have the number 1.2. So our 1.2 is going to go right about here, 1.2. So based on the numbers we have, we know the correct answer has to be negative 1.25, negative 3/4, 0.5, 2/3, and 1.2. Do we have any of these answers that make sense based on what we know? Yes, we do. The correct answer is going to be A. Something else the TEAS is going to test you on is comparing numbers using greater than, less than, and equal to when it comes to your rational numbers. When we perform solutions like inequalities, we're going to start to see things like less than or equal to, greater than or equal to as well. But in this particular cases, we're only focusing on 3 of them: less than, greater than, and equal to. Here's a quick tip that I want you to remember when you're taking your TEAS when it comes to less than or greater than and remembering which sign you need to use. I want you to think of a very hungry alligator or a hungry hippo or maybe even Pac-Man. They're always going to want to eat the larger number. Because I live in Florida, I'm going to use the alligator analogy. So the alligator is going to want to eat the greater number. So we have 3 and we have 5 here as an example. So is 3 greater than 5? Absolutely not, right? 3 is less than 5. So our little gator here is wanting to eat that number 5 because it's very, very hungry. So we're going to use the less than sign, right? His mouth is going towards the higher number. So let's take a look at our numbers. So we're comparing 0.75 to 3/4. So when we look at our number line, we have 0.75 right about here. And when we divide 3 by 4, it's also going to give us 0.75. So in this case, we can say that 0.75 is equal to 3/4. Our next example, we have negative 1/1/10 and 2 1/5. So negative 1/1/10 is going to give us about negative 1.1, and 2/5 is going to give us about 2.2. So is our negative 1.1 greater than 2.2? Absolutely not, right? So we can say that negative 1/10 is less than 2 1/5. Now looking at our last example, we have 1.2 and negative 0.8. So 1.2, we're going to plot her about right here. And negative 0.8 is going to go right about here. So is 1.2 greater than negative 0.8? Absolutely. So we're going to go ahead and use the greater than sign, as we know that 1.2 is greater than negative 0.8. So our question states, which of the following is not true? So we're looking for the one that's not true. So we're going to break each one of these down. So we have 3/4 is greater than 0.75. Well, if we convert 3/4 to a decimal, that gives us 0.75. 0.75. Is 3/4 greater than 0.75? Absolutely not, right? We know that this one is not true, but let's go ahead and move through everything else. So next we have -1/2 is greater than -0.6. So using our number line, we know that -1/2, when we convert it to a decimal, is -0.5, and we have -0.6. So 0.5 would be here, 0.6 would be right about here. So is -1/2 greater than -0.6? Yes, absolutely. So we can automatically eliminate that answer. So next we have 0.5 is greater than 1/3. So as we know, we have 0.5, and then 1/3 is going to be 0.3 with a little line above it. So is 0.5 greater than 1/3? Yes, absolutely. So we can automatically eliminate that. And then our last is 2.5 is greater than 5/3. So when we convert 5/3, we get 1.66, so on and so forth down the line, and we have 2.5. So 2.5 would be about right here, 1.6 would be right here. So is 2.5 greater than 5/3? Yes, absolutely. So the correct answer is A. 3/4 is not greater than 0.75. So on the ATI TEAS, it's going to be crucial that you understand some vocabulary terms when it comes to algebra. Here you can see we have an algebraic expression, 15x plus 5. There are going to be 4 key terms that are consistently going to be used when you're taking your test. It's going to be coefficient, variable, term, and constant. So let's begin with the term variable. So variables are elements within an expression whose values are not fixed. They represent letters of unknown quantities. In our given example that we have here, the one variable we have, x, represents the quantities that are not immediately known without needing additional information. Next up, we have our constant. So in our example, the constant is the number that is represented by the number 5. It's labeled as a constant because it stands alone without any variable attached to it. Unlike variables, whose values might change depending on specific conditions or inputs, a constant remains the same within the expression. Therefore, any number that appears by itself, not accompanied by a variable, is considered a constant in algebraic expressions. Next up, we have coefficient. And a coefficient is a number that multiplies by a variable within the expression. So for instance, in our example, our coefficient is actually 15. Coefficients and variables are paired together in multiplication relationships. And when they are written, that number, our coefficient, always precedes the variable. And finally, let's talk about terms. So in an algebraic expression, a term refers to a component that is delineated by addition or subtraction symbols. So for example, in our expression, 15x and 5 each represent distinct terms. So essentially, terms are the building blocks of an algebraic expression, excluding the operators, that is our addition and subtraction themselves. Although the concept of terms might not be the primary focus, it's crucial to understand because it underpins the structure of algebraic expressions. Another important concept that you're going to need to know is inverse arithmetic operations. So this principle revolves around the question, what do we add, subtract, multiply, or divide into a number for it to result in 0? To illustrate this concept, consider an example where we're looking to find what can be added to a positive number in order to result in 0. Given that x is a positive number, the additive inverse would be negative x. It's negative counterpoint. Therefore, if you add x to negative x, you're going to get 0. They essentially cancel each other out. In our next example, we're dealing with a negative value, negative x. To find what needs to be added to achieve 0, we use that additive inverse concept, meaning that we need to add the opposite. So negative x plus positive x is going to equal 0, demonstrating the inverse property of addition. Not too bad, right? Now let's dive into inverse property of multiplication. This principle is centered around identifying what number, when multiplied by another, is going to yield 1. Essentially, any number times its multiplicative inverse or reciprocal equals 1. So for our first example, consider the letter B, where B is a whole number and not a fraction. It's actually quite helpful to represent B in its fractional form as B over 1, where any whole number can be expressed as a fraction over 1. To find the reciprocal, we invert the fraction, making the denominator the new numerator and the numerator the new denominator. Therefore, the reciprocal of B is actually 1 over B. To verify this, let's multiply B in its fractional form as B over 1 by its reciprocal 1 over B. When multiplying fractions, we multiply the numerators together and the denominators together. Starting with our numerator, we have B times 1 is going to give us B. And with our denominators, we have 1 times B is also going to give us B. This is ultimately going to give us B over B, which further simplifies into the number 1. We may also encounter a fraction of 1 over B. In order to identify the reciprocal, we simply flip the fraction, resulting in B over 1. And just like we did in our previous example, when we multiply our numerators and our denominators together, we are going to simplify it to B, or that's also going to equal 1. Let's take a look at some examples for solving equations using one variable. So when we're performing these operations, we want to perform the opposite or inverse operation of whatever we are doing on one side of the variable to the other side of our equation. So our first example, we have x minus 6 equals 13. So we want to isolate x in order to find out what that number is. So what we're going to do is, just like we did before, we're going to do the inverse. So we have a negative 6. We're going to add a positive 6 to both sides. Adding a positive 6 is going to give us x equals 19. We just solved our first equation. In our next example, we have 3x plus 9 equals 0. So again, we want to isolate x first. So we do that by minusing 9 from both sides. Because here we had a positive 9. We want to make sure that we minus 9 in order to achieve 0. Once we do that, we're going to get 3x is equal to negative 9. And now we need to again isolate that x. So how are we going to do that? We are going to go ahead and divide by 3 on both sides in order to get rid of that 3 coefficient before our variable. That is going to give us x is equal to negative 3. Our next example, we have 15 equals 5m. So again, we want to isolate that variable. That's our m. So we're going to divide 5 by both sides, and that is going to give us 3 is equal to m. And our last example may seem a little bit tricky, but actually it's really quite simple. We have 11 is equal to w divided by 3. So again, we want to isolate our variable. We want to get that w on one side by itself. In order to do that, we're going to multiply each side by 3 because that is the inverse operation, and that is going to give us 33 is equal to w. Not too bad, right? So next up, we're going to solve proportions with one variable. So you're going to see two fractions with an equal sign between them, and you're going to have to solve for whatever the variable is, whether it's x or another letter. So in order to do this, we're going to cross multiply fractions to obtain an equation with one variable. So we do this by cross multiplication of our fractions. Our first problem is going to give us 10x is equal to 60. So now we have an algebraic expression and we just need to solve for x. So we do so by dividing each side by 10, and that is going to give us x is equal to 6. Let's try another example. So down here we have x over 3 is equal to 4 over 6. So again, we are going to cross multiply our fractions, and that is going to give us 6x is equal to 12. We have our algebraic expression, so we're going to go ahead and we're going to divide each side by 6 to isolate x, and that is going to give us our correct answer of x is equal to 2. For our next example, we have 7 over x is equal to 14 over 28. So again, we're going to cross multiply our proportions, and that is going to give us 14x is equal to 196. We're dealing with big numbers now, right? We are again going to isolate our x by dividing each side by 14, and that is going to give us our correct answer of x is equal to 14. Hopefully this has helped bridging some gaps in understanding how we cross multiply proportions. So let's move on to our final example. So we have 5 over x is equal to 10 over 20. So we're going to go ahead and cross multiply. This is going to give us 10x is equal to 100. And of course, we're going to divide each side by 10 in order to isolate x. And that is going to give us our final example of x is equal to 10. So let's talk about estimation. On the ATI TEAS, you're going to have to use your best judgment in regards to length, weight, and capacity when it comes to various items. So starting with the estimation involving length, you're going to be using metric system conversions. It is a crucial skill that you're going to need to know for the ATI TEAS as well as healthcare. So choosing the appropriate unit of measurement depends on the object that you are measuring. If you haven't already done so, I highly recommend that you go check out my video on metric conversions because it's going to help you break down the differences between each unit and how we establish each one. But let's take a look at how the ATI TEAS is going to test you when it comes to this. So when it comes to length, there's a couple different things that you will need to know. You're going to need to know meter, centimeter, millimeter, and kilometer. So starting with the meter, just to give you real life examples, 1 meter tall is about the height of a doorknob. So when you look at your doorknob, that is about the height of 1 meter. When we're talking about centimeter, we're talking about the width of a paper clip. That's approximately 1 centimeter. When we're talking about millimeter, that is approximately 1 millimeter is the diameter of a grain of salt. It's really tiny. It's not the length of the grain of salt, it's that diameter that cut through. And then lastly, with kilometer, when we think of kilometer, 1 kilometer is equal to an airport runway. So if you've ever been in an airplane, you know that runway is very long. That is approximately 1 kilometer. Next up, we have weight. So approximately when it comes to weight, a gram is equal to the weight of a paper clip. So that paper clip's not very heavy, right? So it's very light. So that's approximately 1 gram. Next up, we have milligram. So 1 milligram is essentially the same weight as a pinch of salt, so not very big. And then lastly, kilogram. So 1 kilogram is approximately the weight of 1 bag of rice. And last up, we have capacity. So 1 liter, if you look at those large water bottles, even like this water bottle, right? This water bottle is approximately 1 liter. Then we have milliliter. So this is huge in healthcare. So 1 milliliter is just like a small medication dropper amount of liquid. And then lastly, we have a kiloliter. So a kiloliter is approximately the entire capacity of a pool of water. So let's take a look at some examples of how this will be tested on the TEAS. So starting with question 1, what is the best estimate for a length of a standard kitchen knife? So we're talking about the length. So is it 20 millimeters, 200 centimeters, 30 centimeters, or 3 kilometers? So taking a look back at our examples, we know that a standard kitchen knife is not going to be as small as 20 millimeters, right? That's that diameter of our grain of rice. So we can automatically eliminate A. And it's definitely not as long as 200 centimeters. Think about it. 200 paper clips widths. That's way too long, so we can automatically eliminate that as well. And then of course 3 kilometers, that would be 3 airport runways. So we definitely know that that is also not our correct answer. So out of all the ones that we have available to us, C, 30 centimeters is going to be the most correct answer. Our next question is, what is the most appropriate unit and estimate for the weight of a car? Is it A, 1,500 grams, B, 1.5 kilograms, C, 1,500 kilograms, or D, 15,000 milligrams? So in order to answer this question, we have to know that cars are significantly heavier than small objects measured in grams and milligrams. So we can automatically eliminate anything that has grams or milligrams from our question. So now we're just left with kilograms. So if you didn't already know, 1 kilogram is actually equal to 2.2 pounds. That's actually a conversion that's going to be really important for you to know. So if you think about it, 1.5 kilograms is just a little over 3 pounds. So we can automatically eliminate that Based on all of the answers that we have available to us, C, 1,500 kilograms is going to be the most correct answer. And our last question states, which is the closest estimate for the total volume of a bathtub filled with water? Is it A, 150 milliliters, B, 150 liters, C, 15 centiliters, or D, 1.5 kiloliters? So again, using our deduction of real-world examples of how to measure objects, we know that a bathtub with water has to contain way more than 150 milliliters. So we can automatically eliminate that. And of course, 15 centiliters isn't going to cut it, so we can eliminate that. So we're left with 150 liters and 1.5 kiloliters. Well, when you think about it, 1.5 kiloliters is going to be excessively more than what we're going to be able to fill up a bathtub with. Remember, 1 kiloliter is equal to the size of a swimming pool, the amount of water that's in that swimming pool. So we can automatically eliminate that. So based out of all of the answers that we have available to us, B, 150 liters is going to be the correct answer. So as you can see on your screen over here, this is a little cheat sheet of everything that you're going to need to know in regards to how to translate words into algebraic expressions. So let's go over those crucial expressions that are going to be pivotal in solving algebraic word problems. So when you come across the phrase 4 times a number, you're going to automatically translate this into 4 times x, where x is going to represent that unknown quantity that we have to figure out. For expressions like 4 more than a number, that is translated into x plus 4. Something to make sure you have careful attention to is when you see things like 4 less than a number. It can be easy to interpret this as 4 minus x, but that's actually incorrect. The correct translation is x minus 4, despite that initial position of 4 in the sentence. So be very careful when you come across word problems like this. For a phrase such as 4 times the difference of 2 numbers, it's understood that 4 is going to be multiplied by the difference between x and y, or it's going to be 4 parentheses x minus y, highlighting the importance of placing that x minus y within parentheses and the 4 on the outside. When you see terms like sum and mentioned within our word problem, we automatically associate that with the sum of 2 numbers. So this can be written as x plus y. In contrast, the difference between 2 numbers would be x minus y. If you encounter words like product of 2 numbers, it's going to refer to the multiplication of x and y. And then lastly, if you see words like is or equals, that's just a fancy way of saying our equal sign. These expressions are going to be fundamental when it comes to algebra and mastering that translation into mathematical terms to effectively solve your word problems. Let's take a look at some examples. So our first practice question is, if 6 more than a number is 14, what is the number? So let's break this down, starting from left, working our way to the right. So 6 more than a number is x plus 6. So then we have the word is. Is just, of course, just a fancy way of saying our equal sign. And then lastly, we have 14. And of course, 14 is going to be 14. So now we just need to put our problem together. So we have x plus 6 is equal to 14. Now we just need to solve for x. So we do so by minusing 6 from both sides, and that is going to give us x is equal to 8. Our next example states 3 times a number equals 45. What is our number? So again, we're going to break it down. So 3 times a number is going to be 3x. Then we've got equals. It pretty much just tells us what it is, right? Equals is equal to equal sign. And then lastly, 45, again, 45 is just 45. So now we just need to put our equation together. So we have 3x is equal to 45. We need to isolate our x in order to find the number. So we're going to divide both sides by 3, and that is going to give us x is equal to 15. All right, now that we get the hang of this, let's see if we can figure out these more complicated problems. So we're going to start off with, again, solving our equation from left to right, breaking it down. So 5 times the difference of two numbers is 35. If one of the numbers is 10, what is the other number? So again, we start with 5 times is the difference of two numbers. So that is going to be 5 with parentheses x minus y. So we've got our first part. We have the word is, so that is our equal sign. And then we have the word or the number 35. Well, it also tells us one additional thing, right? It says one number is equal to 10. So that gives us our new equation. So we can say 5 parentheses x minus 10 is equal to 35. Now we just need to solve. So in order to solve this, we have to multiply our 5 by everything within inside our parentheses. So we're going to multiply 5 by x, and we're going to multiply 5 by 10. So we've got 5x minus 50 is equal to 35. Now we need to start isolating our x. So we are going to add 50 to both sides. That is going to give us 5x is equal to 85. And now we are going to divide 5 by both sides in order to isolate our x. And that is going to give us x is equal to 17. Not too bad. So our next question states the product of 8 and the sum of a number and 2 equals 64. What is our number? So let's break this down working left to right. So the first thing we have is we have the word product. So as we know, product is going to be our x and it's going to be our y multiplied together. So we know that we have the product of 8, so that's the start of our equation, and it's going to be the sum of a number and 2. So that's going to be x as our number plus the number 2, and we're going to close our parentheses sign. Next we have the word equals, so of course equals is equal to equal. And then lastly we have the number 64. So 64 is 64. So now we're going to do the same thing like we did before, and we're going to multiply our 8 by everything within our parentheses. So we're going to multiply 8 by x, and we're going to multiply 8 by 2. So that's going to give us 8x plus 16 is equal to 64. Now we need to start isolating our x, right? So we're going to minus 16 from both sides. That's going to give us 8x is equal to 48. And then we are going to divide 8 by both sides to isolate our x. So x is going to be equal to 6, which is the answer to our word problem. So let's work on a little bit of a longer word problem. So this word problem states a hospital uses 2.5 liters of sanitizing liquid across 5 examination rooms every day. If a bottle of sanitizing liquid contains 500 milliliters, how many bottles are used per day? So first, right off the bat, I'm just going to eliminate the fact that we have across 5 examination rooms every day because it has nothing to do with our problem. So we're solely focusing on the fact that we have a use of 2.5 liters of sanitizing liquid and the fact that each bottle contains 500 milliliters. So we have to figure out how many bottles are used per day. So the very first thing when we're looking at this problem is that we have liters and we have milliliters. So we're going to have to convert our liters to milliliters in order to solve this equation. So again, if you haven't watched the metric conversions, highly recommend that you watch it so this makes sense. So 2.5 liters is equal to 2,500 milliliters. So now we're just going to plug and play. So we know that we have 500 milliliters, and that is going to be multiplied by B because we need to know how many bottles we need, right? And that is going to be equal to 2,500 milliliters. This is our equation. We have 500 milliliters per bottle. That's represented by the B that we added into our equation, and it's going to be equal to 2,500 milliliters. Now all we have to do is isolate our B. So we do this by dividing both sides by 500, and that is going to give us B is equal to 5 bottles. So they need a total of 5 bottles in order to make it through every day. Our next question states, Sarah trains for a marathon by running 15 kilometers every day. If a marathon is 42.195 kilometers long, how many days of training does it take Sarah to run at least the distance of a marathon? So we have two numbers here. We know that she runs 15 kilometers every day. And then our second number is we know that a marathon is 42.195 kilometers, and we need to figure out how many days it's going to take Sarah to run this. So we're just going to plug this into an equation. So we're going to have 15 kilometers over 42.195 kilometers is equal to 1 day over x day. So what I like to do when I'm doing word problems, especially proportions and ratios, is I like to keep the same terms on each side. So on this side, we know that these are the kilometers that she's going to run. And on this side, well, this is the time, right? How many days? So this is like I had to kind of keep it simple and to keep it organized. So as always, we're going to cross multiply. So we're going to do this by cross multiplying our numbers. That's going to give us 15x is equal to 42.195. And now we're just going to divide each side by 15 in order to isolate our x. And that is going to give us 15 is equal to 2.813 days. Or if you were required to round up, it's approximately 3 days. So the correct answer is 2.813 or 3 days. So next up, let's talk about percent proportions, where relationships between a part and its whole matches the relationship between percent and 100. This allows us to create an equation or proportion to represent that relationship. So the formula that we are going to use, as you can see here, is over of is equal to percent over 100. With this formula in hand, we can tackle a lot of problems focusing on percents. Let's take a look at our examples. So looking at our first practice question, we have 18 is what percent of 42? So we break this down. We have our is, that's 18. We're trying to figure out what a percent is because we have the words what percent, and we have our of, which is of 42. So now we're just going to plug in our numbers. We have 18 over 42 is equal to what percent, right? So that's going to be our x over 100. Now we're just going to cross multiply. So we're going to multiply 42x is equal to 1,800. We need to isolate our x by dividing both sides by 42. And that is going to give us x is equal to 42.86%. So moving on to our next question, we have 20 is what percent of 45? We're going to use the same formula. So we have our is, that's 20. We're trying to figure out what percent, that's our x. And then lastly, we have 45. So now we're just going to plug in our numbers. So we have 20 over 45 is equal to what percent, that's our x, over 100. So now we're just going to cross multiply. So we're going to multiply here, we're going to multiply here. That's going to give us 45x is equal to 2,000. Then we're going to isolate our x by dividing both sides by 45. And that is going to give us x is equal to 44.44%. And now with our last initial example, we have what percent of 12 is 27. So this one's a little bit different, right? Let's just break it down working left to right. So we have what percent, that's our x, that's what we're looking for. 12, so that's our of, is 27. So now we just need to plug in our numbers. We have 27 over 12 is equal to x over 100. Now we're going to cross multiply. That's going to give us 12x is equal to 2,700. We're going to divide both sides by 12, and that is going to give us our answer of 225%. Let's take a look at some longer word problems when it comes to percentages. So our first problem is, in a town survey, 250 people said they preferred tea over coffee out of the total 500 respondents. What percentage of the respondents preferred tea? So again, we're just going to work this out working left to right. So we know that our is our 250 people. Those are the people that prefer tea over coffee. Our of is the total amount of people that were surveyed, right? So that's 500 respondents. And then what percentage of the respondents preferred tea? So again, what percent? That is what we are looking for. That is our x. So now we're just going to plug in our numbers. 250 over 500 is equal to x over 100. Now we're going to cross multiply. So we're going to cross multiply here and cross multiply there. That's going to give us 500x is equal to 25,000. We're going to divide both sides by 500 in order to isolate our x, and x is going to give us 50%. Our next example states a store sold 120 out of 150 chairs they had in stock. What percentage of the chairs were sold? So again, we're just breaking this down. So working left to right, a store sold 120. So that is our is. Out of, there's our word of, 150 chairs. What percent is what we're looking for? That's our x. So let's go ahead and plug this into our equation. We have 120 over 150 is equal to x, because we're trying to figure out what percent, over 100. So now all we have to do is cross multiply. That gives us 150x is equal to 12,000. We're going to divide each side by 150, and that is going to give us x is equal to 80%. So 80% of the chairs were sold. Now let's take a look at word problems using ratios and proportions. So ratio and proportions are problems that are one and the same, and they can be solved with the same cross multiplication that we've been using this entire video. So starting with our example, we have Carmen can read 4 fictional books in 10 hours. Assuming all the books are the same length, how many hours would it take her to read 50 fictional books? So step 1 is we want to identify our knowns and our unknowns. So what we do know is that Carmen can read 4 fictional books in 10 hours. We know that, right? What we don't know is how many hours it's going to take her to read 50 fictional books. So our knowns are she can read 4 fictional books in 10 hours, and we're trying to figure out how long it's going to take her to read 50 fictional books. Our unknown is that amount of time that it's going to take her to read those 50. So for step 2, we need to plug in our proportions into our equation. So we have 2 proportions, and I've written them out here. We have 4 books in 10 hours, and we have 50 books in X hours. So like I said before, what I like to do is keep everything organized. So on the left side of our equation, I have all of our books, and on the right side of our equation, we have our time. So what I did is I plugged in 4 books into our numerator on the left, and 10 hours into our numerator on the right. On the bottom, we're trying to figure out how long it's going to take her to read those 50 books. So I put 50 books underneath our 4 books in the denominator on the left, and I put X hours, which is what we are trying to figure out, in the denominator under our 10 hours numerator on the right. So now all we have to do is we have to solve for the proportion. So we use that cross multiplication that we've been doing. So we would have 4 times x would give us 4x, and we have 50 times 10 would give us 500. And then of course, in order to isolate x, we would just divide each side by 4, and that would ultimately give us x is equal to 125 hours. Let's take a look at some examples of this in real time. So our first problem states the ratio of boys to girls in a class is 8 to 7. If there are 48 boys, how many girls are in class? So what we know is we have an 8 to 7 boys to girl ratio, and we have 48 boys. What we don't know is how many girls are in the class. So that's what we're trying to figure out. So like I said before, what I want to do is organize everything it is that I need to know. So I'm going to put the boys on one side, and I'm going to put the girls on the other side. So I know that there is a 8 to 7 ratio of boys to girls. Those are going to be my numerator on both sides of my equation. I know that I have 48 boys. What I don't know is how many girls I need. So now that I have my equation, it's again just a sense of cross multiplication. So that's going to give us 8x is equal to 336. We need to isolate for x on both sides by dividing by 8, and that is going to give us the number 42. So we know we have 48 boys in class, and the number we didn't know is now we have 42 girls in that class. Our next example is Calvin can make 16 cakes in 8 hours. How many cakes can he make in 16 hours? So again, what do we know? We know that Calvin can make 16 cakes in 8 hours. What we don't know is how many cakes he can make in 16 hours. So we're just going to plug this in. Again, organizing it. I like to keep everything organized. We're going to put cakes on one side, and we're going to put our time on the other side. So starting with our ratio, we have 16 to 8, right? So we're going to put 16 in our numerator on the left, and we are going to put 8 in our numerator on the right. And now we know at the bottom he needs to make a certain amount of cakes within 16 hours. So we know what the hours is on the bottom. We just need to figure out how many cakes he's going to be able to make. So now that we have our equation, we're going to cross multiply. And we do this by saying 8x is equal to 256. We need to isolate our x on both sides by dividing by 8. And that is going to give us x is equal to 32 cakes. So within 16 hours, Calvin should be able to make 32 cakes. So in a hospital ward, the ratio of nurses to patients on a particular day is 1 to 4. If there are 8 nurses on the ward, how many patients are they going to be responsible for? So we know we have 8 nurses, and we're trying to figure out how many patients they're going to have. So again, we're going to organize it. So we're going to put our nurses on the left, and we're going to put our patients on the right. And we're just going to plug in our ratios. So we have 1 nurse to 4 patients. We know that we have 8 nurses. We're trying to figure out how many patients they're going to have on the floor. So again, we're going to cross multiply. That is going to give us x is equal to 32. There's no additional math that needs to take place, so we know that if we have 8 nurses on the floor, we should have 32 patients as well. So here's a really good one for those of you who are going to nursing school. So a prescription requires medication to be given at a ratio of 2 milligrams per 10 kilograms. That's our first ratio. If a patient weighs 70 kilograms, how many milligrams is that patient going to receive? So again, we're going to organize our information. We're going to put our med here on the left-hand side, and we're going to put our kilograms, which is our patient's body weight, over here on the right-hand side. And we're just going to plug in our ratios. So we have 2 milligrams of med for 10 kilograms of patient. We know that we have a 70 kilogram patient, so we need to figure out how much med they're going to receive. And now we're just going to cross multiply. So that's going to give us 10x is equal to 140. We're going to divide each side by 10 in order to isolate x, and that is going to give us x is equal to 14 milligrams. So for this patient, we need to make sure they get at least 14 milligrams based on their body weight. Next, let's talk about rate, unit rate, and rate change. I group these concepts together with ratio and proportions because they follow the same principles. So rate is essentially a ratio that illustrates the connection between 2 quantities with different units, effectively demonstrating how one quantity relates to another one when the units are going to differ. Whereas with a unit rate, this particular form of rate is going to be where the denominator is 1 and is essentially expressing the same amount of a single unit. So let's explore how each example clarifies this concept. So with our first example, rate, we have 36 miles in 4 days. How many miles per day? So again, we organize by putting our miles on one side and we put our days on the other side. So we know that this individual is going to be able to drive 36 miles in 4 days. That is our first ratio. Our next ratio is how many miles per day. So we know that we have 1 day and we're trying to figure out how many miles. So we plug this into our equation and of course we're going to cross multiply. So that's going to give us 4x is equal to 36. We need to isolate x in order to figure out our equation. So we're going to divide 4 by both sides, and that is going to give us x is equal to 9 miles per day. Next up, we have unit rates, and we're usually talking about unit rate, we're talking about money. So in this case, we have $96 in 8 hours. How many dollars per hour? So we know we get $96 in 8 hours. Now we've got to figure out in each hour, how much money am I getting? So we're going to go ahead and plug that into our equation. Remember, keep everything the same. We're going to have dollars on one side, and we're going to have hours on the other side. And we're going to get 96 over x is equal to 8 over 1. We're going to cross multiply. That's going to give us 8x is equal to 96. We have to isolate x, so we're going to divide each side by 8, and that is going to give us x is equal to $12 per hour. So how do we solve word problems with inequalities? So inequalities is a mathematical expression that describes relationships between two values when they are not even. So instead of saying two values are exactly the same like we do in equations, inequalities is going to tell us if one value is greater than, less than, greater than or equal to, or less than or equal to another value. This helps us understand the range of limits within a certain quantity that can exist. There are 4 main symbols that you're going to see when it comes to inequalities. First up, we have the greater than symbol, and that's going to indicate that the value on the left side is larger than the value on the right side. Next, we have the less than symbol, and this is going to indicate that the value on the left side is smaller than the value on the right side. Next, we have greater than or equal to, and that's going to indicate that the value on the left side is either greater than or equal to that value that's found on the right side. And you've guessed it, you're right, that less than or equal to is the exact same thing. It's going to indicate that that value on the left side is either less than or equal to the value on our right side. So here's a quick tip for remembering less than and greater than signs. Think of each sign as either a hungry, hungry hippo or a Pac-Man, or for me, because I live in Florida, I always think of an alligator. They're all hungry, right? They all want to eat as much as they possibly can. So their mouths, if you think about that little sign as a mouth, is always going to eat the greater number, right? So it's either going to be greater than or it's going to be less than, depending on which way they're eating it. So hopefully that kind of helps trigger your memory when you're trying to figure out which one is which. So let's take a look at our first example. We have a hospital elevator has a maximum weight capacity of 2,000 pounds. If there are already 3 people on the elevator with a combined weight of 460 pounds, write an inequality expressing the possible weight that may be added to the elevator. Use W to represent the weight. So we're given that the elevator has a max capacity of 2,000 pounds. That's the total amount of weight that can be in that elevator, and you cannot go above that threshold. So in scenarios where we're dealing with maximum limits, the appropriate mathematical symbol to use is going to be less than or equal to, because the total weight can reach up to 2,000 pounds, but it's not going to be able to surpass it. So we either have to have less than or equal to what that weight is. Next, we want to make sure that we add our weight, so we know that we have 2,000 pounds is going to be acceptable. Given that there are 3 people already on the elevator and they have a combined weight of 460 pounds, we actually have to incorporate that within our equation. So I'm going to add 460 over here to the left side of the equation. And then of course, we have to incorporate W, because W is going to denote what that weight is going to represent for that additional weight to not exceed that 2,000 pounds. So that's going to be W plus 460 is less than or equal to 2,000 pounds. Now we just have to solve our equation. So we're going to minus 460 from both sides in order to isolate W. And that is going to give you W is less than or equal to 1,540 pounds. So at most, the most that they can add to that hospital elevator is going to be 1,540 pounds, with those additional people that are already on the elevator. Our next example states, to qualify for a scholarship, students must score at least 85% on their final exam. If X represents the student's score on the final exam, which inequality represents the score of students who qualify for the scholarship? So as we know, these students have to have at least 85% on their exam. So we're going to put 85% over here on the right side of our equation. And now we need to figure out what we need to solve for X. So they have to have at least 85%. So that means that they have to have either greater than or equal to 85%. So I'm going to go ahead and plug that into my inequality, and that's going to give us our equation for this problem. X is greater than or equal to 85% in order for the student to get the scholarship. Let's take a look at a little bit more of a complicated problem. So a factory has a fixed operating cost of $3,600 per day plus costs of $1.40 per product produced. If a product sells for $4.20, what is the least number of product that must be sold per day to make a profit? So to make a profit, we have revenue received needs to be greater than the cost needed to make it. So that's going to give us our revenue is greater than costs. That's very important. Now we need to create an inequality for this. So we already know that X is going to equal our products produced. So for cost, there's a fixed cost of $3,600 per day. So we're going to put that on our cost side. $3,600 per day. And we know that we have to have a cost of $1.40 times X for each product that we're making. So now we've got our revenue is greater than $3,600 plus 1.4x. That's how much it's going to cost us to make these products. Now we need to figure out our revenue. So our revenue, we have it right here. It states that we sell the products for $4.20. So we're going to plug in that $4.20 on the one side. And we also need to plug in X because X is our products that are being produced. So now we have our equation. 4.2x is greater than $3,600 plus 1.4x. So now we need to start isolating for x. So how are we going to do this? Well, we need to get x on one side. So we're going to minus 1.4x from each side, and that is going to give us 2.8x is greater than $3,600. We need to isolate for x. We do so by dividing each side by 2.8, and that is going to give us x is greater than 1,285.71. So if we round up, we need to sell at least 1,286 products in order to make revenue for this factory. The last topic that we're going to talk about is direct proportion and constant of proportionality. On the ATI TEAS, you're going to be tasked with identifying each one of these concepts. We're going to briefly discuss it because it is a very small portion of your exam, but it is something that you're going to need to know. So starting with direct proportion, this is going to describe a relationship where one quantity increases and the other quantity is also going to increase at a consistent rate. Conversely, as one quantity decreases, the other quantity is also going to decrease, maintaining that consistent ratio. So this constant rate is known as constant proportionality, and it's symbolized with the letter K. It quantifies that direct relationship between two quantities. So in mathematical terms, when we're looking at this, the two quantities of x and y are going to be directly proportional. So we're going to use the equation y is equal to kx, where k is that constant proportionality. This means that every unit that increases in our x is also going to increase in our y when it comes to those k units. So I have a little graph down here to kind of help that make sense. So whatever x is, in our first example, we have y equals 5x. Whatever x is going to be, it's going to be multiplied by 5 every single time. So you're going to see this kind of linear equation when it comes to these direct proportional equations. So imagine that you have a bag of marbles. And for every marble that you take out, you get 2 candies. If you take out one marble, you get 2 candies. If you take out 2 marbles, you get 4 candies, so on and so forth. This is direct proportion because the more marbles that you take out, the more candies you're going to get. And it's always going to increase at the same amount. In a non-directly proportional relationship, the correlation between two variables isn't going to be linear like we saw with our direct proportional changes. This means that the ratios are not going to change at the same time and consistently. Imagine that you're pouring water on plants. The more water that you pour, the taller the plant is going to grow. But it's not always going to be the same like we have with our predictability when it comes to the candies in the marbles example. Sometimes you might pour just a little bit of water and the plant's going to grow really, really big, right? And other times you're going to pour just a little amount of water and the plants aren't going to grow that much. This is what we like to use in terms of non-directly proportional relationships because there isn't a steady pattern that tells us exactly how much that plant is going to grow based on the water that it gets. In these relationships, variables interact in a more complex way. We typically see y is equal to mx plus b because these equations tend to be more slope-based than we saw with our linear equations in our direct proportional examples. In this case, only if b is equal to 0 would we actually have a direct proportional relationship. So I've listed a couple of equations here on your slide to help you kind of identify the differences between these two relationships so it's easy to answer these questions when you're taking the TEAS. So let's identify the differences between direct and non-direct proportional relationships. So our first example, we have y is equal to 2x. So as we know with our direct relationships, we're going to have y is equal to kx. And with our non-direct proportional relationships, we're going to have things like y is equal to mx plus b. So in this case, we have y is equal to 2x. So as we increase our x, we're always going to have the same number of increase because of that 2 coefficient before our x. So this is an example of a direct relationship. Next up, we have y is equal to 8. Well, we have no variable here, right? It's just y is equal to 8. That's constant. It's a fixed number. It's not going to change. So this is actually going to be a non-direct relationship because we need that variable in order to make that change. Next up, we have y is equal to 3x plus 10. This is a great example of y is equal to mx plus b because even if we increase our x, it's not going to be the same consistently every single time. So because we have that additional term, that 10 on the end. So this is an example of a non-direct relationship. And then lastly, we have y is equal to 5x. So 5 times x, as many times as we're going to multiply something by that 5 with that x, it's going to be the same every single time. So we're going to have a linear equation. So this is a great example of a direct relationship. Let's start off by talking about mean, median, and mode. So our mean is the average number of a data set. Our median is the middle number of a data set. And our mode is going to be the most frequent number of a data set. So when you are taking your TEAS, they are going to give you a list of numbers. That is going to be your data set that you have to compare in order to find these values. What I highly recommend that you do when you're taking your TEAS is to place those numbers in numerical order from least to greatest. Trust me, it's going to save you a whole lot of time as you're doing your calculations. So I've already done that here for you in the data set that was provided. So starting with our mean, remember that's the average. We have to figure out the average of all these numbers. Our very first step that we want to do is we want to add all of our numbers together. So based on our data set, if we were to add all of these numbers together, we're going to get 127. But we're not done yet. We have another step that's very important. Once we figure out what the overall sum is of all these numbers, we need to divide it by the total numbers that are within our data set. So if we were to add these numbers together, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we have 10 numbers. So we're going to take 127, which was our sum, and divide it by 10, which was the total number of numerical digits that were provided to us. That's going to give us our number of 12.7 or 13 if the TEAS asks you to round it up. So the mean of this data set is 12.7 or 13. Next, let's move on to our median. So the median is our middle number of a data set. So when you think of median, think about when you're driving down a highway, right? There's always something in the middle that is always protecting you from being able to go into the oncoming traffic lane, right? We don't want that. We don't want accident. And when we think of median, we think of middle. Think of that middle median that's down our highway roads. So again, organizing those numbers are going to help save you so much time on the T's. We're going to have to start kind of crossing off numbers from each end until we figure out what our median numbers are. So we would cross off 8 and 18, 10 and 16, 10 and 15, 10 and 14, and look at that. We have an even amount of numbers. So we actually have two middle numbers. So when we have an even amount of numbers, we need to find the average between the two in order to determine what our median is. So if we were to add 2 and 14, that's going to give us 26. You're going to divide that by 2, and that is going to give us 13. So the median for this data set is 13. Now, it's way easier if you have an odd number because, of course, whatever that number is in the middle would be your median. But when you have even numbers, make sure you're adding them together and dividing them by 2. And then lastly, we have mode. So when I think of mode, I think of most. M-O mode, M-O most. Mode is most. It's the most frequent number in our data set. So again, lining them up, save you a whole bunch of time. So if we look here, we have 1 8, we've got 3 10s, 1 12, 2 14s, 1 15, 1 16, and 1 18. What number do we see the most? Well, the number that we see the most is 10. So based on the numbers that we have here, our mode, most number, is going to be 10 as it appears 3 times in our data set. Our first practice question is, you are a nurse in a post-operative unit tasked with assessing the pain levels of 10 patients who have recently undergone surgery. You are using a standard 0 to 10 pain scale where 0 indicates no pain and 10 signifies the worst possible pain. Throughout the day, you record the following pain scores for patients after knee surgery. So as we can see here, we have our patients' rooms, which really isn't something that we have to worry so much about when we're trying to find mean, median, mode, but we have pain scores. These are the ones that are going to be important. So let's start off with finding our mean. Again, we need to put these in numerical order. It's going to save us a whole bunch of time later, trust me. So let's see, the lowest number we have here is 3. So we've got 3, we've got another 3 here, and we have another 3 here. Next we have 4, we've got another 4 here, and another 4 here. After that we have 5, and we have another 5 here. That's all of our 5s. Then we have 6, and our last number is 7. Perfect. Now we got them in order. We're going to save ourselves a whole bunch of time. So with mean, remember, that's our average. So we're going to add all of these numbers together. So if we were to add 3 plus 3 plus 4, so on and so forth, it's going to give us a total of 44. But next, we're not done. We have to divide it by the total number that's within our data set. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have a total of 10 numbers. So we're going to divide 44 by 10, and that is going to give us our mean of 4.4. Next, let's consider our median. So remember, we're driving down the highway. We get a median in the middle of us. Add is our middle number. So again, I've already written the numbers out here for you in numerical order. So now we got to find our middle. So when I'm doing this, what I'm doing is I'm just marking off the ends. So 3, 7, 3, 6, 3, 5, 4, 5. Look at that. Remember, we have an even number of data points, so we have 4 plus 4. Well, 4 plus 4 is equal to 8, divided by 2 is equal to 4, so our median number here is 4. Our last data point that we have to find is mode. Remember, M-O and mode, M-O and most. We're looking for the most frequent number of our data set. So I have it written out here, but I'll just visualize it for you. We have 3 3s, we have 3 4s, we have 2 5s, 1 6, and 1 7. Well, look at that. We actually have 2 numbers that appear most often within our data set. When this happens, it means we have 2 modes. There's no additional addition, subtraction, multiplication, nothing else we need to do. We just know that our mode is going to be both 3 and 4. All right, let's do some practice. A small bakery tracked its daily cookie sales over 1 week and recorded the following numbers: 12, 15, 11, 12, 14, 16, and 12. Calculate the mean, median, and mode of the bakery's daily cookie sales. Now what I did over here in the corners, I already put them in order for you. But it's very important, remember when you're doing this, put them in order, save yourself some time. So mean, we're finding the average. What's the average of all these numbers? So we have 11 plus 12 plus 12 plus 12 plus 14 plus 15 plus 16. So when we add all these numbers together, we're going to get 91. But again, we're not done. We have to divide these numbers by the total numbers within our data set. So we have 1, 2, 3, 4, 5, 6, 7. So we have a total of 7 numbers in our data set. So 91 divided by 7 is equal to 13 cookies. Next, let's figure out our median. So again, our median is our middle number. Driving down the highway, we're looking at that median. So again, I'm going to go ahead and write out all of these numbers here. And now we have to find that middle number. So I'm going to start crossing some numbers out. So 11 and 16, 12 and 15, 12 and 14. And then look at that. Remember, we have an odd number. So automatically, our middle number is our median. So our median is 12 cookies. And then lastly, let's talk about our mode. So again, we're going to write this out, all of our numbers here, to figure out what our mode is. So we have, remember, mode is most frequent number. We have 111, we have 3 12s, 114, 115, and 116. So our mode of this data set is going to be 12 cookies because this is the number that appears most within our problem. Next, let's explore how we determine the range of a data set. Where is the range defined? It's the difference between the highest and lowest numbers of our set. In our initial example, we have a jumbled data set, so we're going to need to organize that to figure out what our highest number is and our lowest number is. So if we organize this, we can see that our lowest number is 2 and our highest number is 10. So as we said, as we're calculating range, we want to subtract our highest number from our lowest number. So 10 minus 2 is equal to 8. So our correct answer for range with this data set is 8. Pretty simple, right? It's going to be really easy when you're taking it on the TEAS. Let's take a look at our other data set. So again, it's just a bunch of jumbled numbers. So we want to make sure that we put that in numerical order from least to greatest. Save ourselves some times later, right? When we organize this, we have 73 as our least number and 96 as our greatest number. So we're going to just subtract the two. 96 minus 73 is equal to 23. So our range for this data set is 23. So let's take a look at a practice question to tie all this together. So the question states a student's scores on 5 math quizzes are as follows: 82, 76, 91, 85, and 88. What is the range of the students' quiz scores? So very first thing we want to do is we want to sort our data set. So we have our lowest number is 76. Then we have 82. And what I like to do is I like to just cross out as I'm moving through, so that way you're not double counting numbers. 76, 82. The next number we have is 85. Then we have 88. And our last number is 91. Now that we've sorted our data set, we know what our greatest number is and our least number is. So our greatest number is 91, our least number is 76, and we are going to calculate our range. We do this by subtracting our greatest number 91 by 76, and that is going to give us 15. So the range of this equation is 15. And look at that, B is our correct answer. So something else that's important when you're taking your TEAS, especially when it comes to range, is going to be distribution of that range when it comes to shape. So first up, we have symmetry. So a distribution is considered symmetric if you can draw a vertical line through the center of its graph, representing two halves that approximately mirror each other. For our first example, let's consider a continuous distribution graph. Here, it appears that the mean is equal to the median. That makes sense, right? Our median would be right down the middle. Our mean is going to be equal to our median. And as you can see, we have an even distribution on our left side as we do our right side. Something else that's important to note here is our graphs peaks. They indicate the frequencies and provide us with our modes. As you can see here, we can observe two prominent peaks, suggesting that we actually have two modes. This leads us to identify this kind of distribution as bimodal, meaning that we have two modes or two frequencies. It's also symmetric, and we have coinciding mean and median values. So in this particular example, this is going to be bimodal, bi meaning two modes. In our next scenario, we have a mound shape, or it's also commonly referred to as the bell shape because of the way that the distribution looks. Drawing a central line down the middle through our graph, it reveals again that symmetry with equal distribution on both sides of that line. Thus, again, it means that our mean is going to align with our median once more. The notable feature here that we didn't see in our previous example was that we only have one highest peak. So this is going to illustrate in this scenario that our mean is going to be equal to our median, which is also going to be equal to our mode. So we would call this kind of distribution unimodal. Uni meaning one mode. It's also symmetric, so we can call this again unimodal. I hope you now see the difference between bimodal and unimodal examples. Next, let's talk about uniform or rectangular symmetry. So this distribution occurs when all categories or classes within a distribution have frequencies that are equal or very close to equal. Observing such a distribution in our first example, we notice that it appears symmetric, with an even split of data on each side of our median. So the symmetry suggests that our mean is likely equal to the median in this distribution as well. However, the concept of mode is going to be somewhat unique when we're looking at this kind of graph. In this case, we have no mode, as we do not have any peaks as we would have seen in our previous examples. In addition, the frequencies don't have to be exactly the same in all classes. There can be slight variations, as we see here in our second example. The distribution maintains symmetry, implying that our mean is still equal to our median. Although the mode is less defined in a uniform distribution due to the equal or nearly equal frequencies of all classes, one could point to multiple modes or consider the entire distribution mode-like for its uniformity, so we actually call this roughly uniform. While it's not perfectly symmetric, a roughly uniform distribution comes close, showcasing an even spread across all of the classes. Lastly, we're going to talk about skewness, everybody's favorite, the most confusing, right? Well, what I want you to do when you're taking your test is I want you to look down at your toes, and I want to notice the way that your toes trend on each side of your foot. In a left skewed distribution, the bulk of the data is off to our left side. So that is where we are going to find our mean. At the point of the slope, we're going to find our mode, right? That's our most frequent number. If you look at your toes on the left side of your foot, your great toe is at its highest, and each toe that follows is going to get slightly shorter, giving you kind of like an arch. This is the same thing that's happening with a left skewed graph. So in this skewed landscape, the mean or the average is going to be positioned a little bit more to the left. The median, which divides the data set into two, is going to be found slightly closer to our mode, but still between the mode and the mean. This arrangement means that half of the data points are going to fall on the left of the median, with the remainder distributed to the right. Conversely, our right skewed distribution is going to be in the opposite direction. Here, the data is going to accumulate mostly on the left side before it starts trending off onto the right. Just like we pictured before looking at our toes, the same thing is happening with our right foot. Our greatest toe is going to be higher on the left side, and as each toe follows, you're going to see that same skewness take place, that same trend. So when you're trying to figure out the difference between your left and right skewed, when you're looking at graphs, I want you to look at your feet. Is it your right foot that it's mirroring, or is it your left foot foot that is mirroring. Again, the mode when it comes to right skewed is going to remain the highest point right here. Our median is going to be slightly positioned to the right, very close to our mode. And then our mean, which is the average of our numbers, are going to pull a little bit further to the right, indicating the skewness. Very important for you to know to your T's. Hopefully now you got it. Let's take a look at our practice question. A researcher is analyzing the distribution of a data set representing a number of daily online orders received by two different products over a month. The data shows two distinct peaks. So that is going to be our keyword here in our practice question. What is most likely the shape of our distribution? Well, we can automatically eliminate right and left skewed, as we know we only really have one peak. So we're only left with uniform and bimodal. Well, uniform, as we discussed, doesn't have any peaks at all, right? It's uniform. It's one straight line across. So we can automatically eliminate that. And if we're thinking about two distinct peaks, we talked about that. Bimodal, two modes. That is our two distinct peaks. So out of all of the answers that we have available to us, the one that makes sense is C, bimodal. Our next question states, a teacher records the test scores of students in a class and notices that the frequencies of scores is evenly distributed across all positive values. Which of the following best describes the shape of the distribution of these test scores? So remember, when we're seeing even distribution, we're looking at one thing in particular. So let's take a look at our examples. Well, right skewed and left skewed, we can automatically eliminate that because, as we know, we don't have an even distribution. It kind of skews off either to the right or skews off a little bit to the left. Next, we have uniform and bimodal. So as we said before in our previous practice question, bimodal means we're going to have two peaks, right? Two modes. So that is obviously not going to be the right answer. Based on everything that we have available to us, knowing that the data set is evenly distributed, the only answer that's going to make sense is A, uniform. Let's take a look at our last question before we move on to probability. So the question states, in a study of household income in a certain region, it was found that most of the data points cluster at the lower end of the income range, with fewer households earning significantly higher income. This results in a long tail to the right of the distribution. How is this distribution best described? So if we're talking about this, we know that the cluster points for the lower end of the incoming range, right, is going to be most of the data, with fewer households earning a significantly higher. So we know that we've got some households, right, having higher data. And then as we start to see income households, it's going to start to kind of long tail off to the right based on what the question is saying. Long tail off to the right. So based on what we have available to us, we have uniform. Well, that doesn't make any sense, right? Because that would mean we would have no modes. It would just be all evenly distributed. So we know that that is incorrect. We have bimodal. Well, we don't have bimodal because we know we don't have two peaks. We have to have two modes. It tells us that our results are going to long tail off to the right of the distribution. So we can automatically eliminate that. Next, we have left skewed. Well, look at your toes. Based on what we just drew, is your left foot the way that it trends down exactly with what we're looking for here? No, right? We would have to have larger numbers to the right of the graph with the smaller numbers trailing down to the left. So we can automatically eliminate that, leaving us with our only correct answer, which is going to be D, a right skewed graph. Now let's talk about probability. In most mathematical scenarios, outcomes are going to be certain, right? If we say 1 plus 1 is going to give us 2. If we multiply 2 by 3, it's going to give us 6. However, sometimes in math, you're often going to be presented with situations that are far from predictable. For this, we use the probability equation, which is the total number of favorable outcomes divided by the total number of possible outcomes. Let's take a look at the simple act of flipping a coin. We can't be certain if it's going to land on heads or tails. And while we can't predict the outcome of each individual coin toss, we do understand some basic principles about it. For example, in a fair coin toss, the likelihood of landing on heads is going to be equal to the chance of it landing on tails. Since there's only two outcomes, heads or tails, each is going to be equally as likely. We would expect that half the flips would be heads and half the flips would be tails, meaning that the probability of flipping heads is 50% or 1/2, and the probability of flipping tails is also going to be 50% or 1/2. Let's dive deeper into this concept using the probability line, which is essentially a number line ranging from 0 to 1. On this scale, a probability of 0 indicates the impossibility of an event occurring, and the probability of 1 guarantees that this event will most likely occur, marking it as complete certainty. This is the reason why the probability line is confined from 0 to 1. Think about it. No event can have a probability lower than 0, as nothing is less likely than impossible. And similarly, no event can have a probability higher than 1, since nothing can be more certain than certainty itself. When we talk about a probability of 1/2, such as with the case with our coin toss, it means that the event has an equal chance of occurring as it does not occurring. If the probability falls below 1/2, the event is considered unlikely, whereas if the probability is above 1/2, it's going to indicate the event is likely to happen. In addition, the TEAS will commonly practice expressing probabilities in various formats, including fractions, decimals, and percentages. They're all going to be used interchangeably. For example, a probability of 0 can be viewed as 0% chance of an event happening. Similarly, a probability of 1/2 can equate to a 50% chance of something happening, and a probability of 1 corresponds to a 100% chance of an event from occurring. Now let's take a look at an example that's a bit more complicated than a coin toss. Now let's take a look at dice. So a standard dice has 6 faces, each numbered 1 to 6. When you roll the dice, each face has an equal opportunity of landing face up, similar to the 50-50 chance that we see with a coin flip either being heads or tails. However, that's where the comparison is going to stop, because unlike a coin, which only has 2 outcomes, the roll of a dice is going to have 6 possible outcomes. The certainty of landing on one of the 6 faces is represented by a probability of 1 or 100%. However, since only one face can be on top after a roll, the probability must be distributed equally among all 6 outcomes. So we divide that by 6. Doing the math, 1 divided by 6 is going to give us 1/6, which can be translated into 0.167 or 16.7%. This value should be positioned in our probability line to indicate the likelihood of rolling a specific number, say maybe a 3. While that suggests that the 3 is unlikely, it is equally probable as to rolling any other number on our dice. I'd like to highlight an important aspect of probability. Remember that probability of landing heads when you flip a coin is 1/2, and the chance of getting tails is also 1/2. When it comes to rolling a dice, the probability of rolling a 1 is indeed 1/6. Now that you tally the probabilities of all outcomes of flipping a coin, the sum is going to be 2 over 2, which is going to simplify to 1. Likewise, summing up all the probabilities for each face when it comes to a dice is going to be 6 over 6, which is also going to equate to 1. The cumulative probability of all potential outcomes for a given event always is going to equal 1 or 100%. This reflects the certainty that one of the possible outcomes will occur. In our last example, let's make it a bit more complicated by introducing a spinner. If our spinner only had 6 sections of equal size, the probability is going to mirror that of rolling a dice. But to make things more interesting, let's increase the number of sections. Now our spinner has 16 equal segments. So what's the likelihood of landing on a number, say 10? Similar to dividing a die, 100% chance among the 6 faces, we're going to evenly distribute that percentage across the spinner's 16 sections. Therefore, the chance that that spinner is going to land on 10 is 1/16, or 6.25%, which again, we can plot on our probability line. It's now evident that landing on a 10 with our spinner is going to be less likely probable than rolling a 3 when we have a die. This is logically given with the number of outcomes based on our spinner and our dice. Now let's add one more layer to this scenario. How do we determine the probability of a spinner landing on a specific color? With our spinner now featuring 5 blue tiles and 11 gray ones, let's delve into the probability of landing on one of those blue tiles. Drawing parallels to previous examples, like the coin flip resulting in 1/2 and the dice resulting in 1/6, we notice a common theme. The numerator from all of these fractions were 1. This is because we were focusing on one singular outcome, such as rolling heads on a coin flip or rolling 3 on a dice. However, in our current scenario, the numerator of this fraction is going to change to 5 because we are reflecting the 5 blue tiles that must meet our criteria for a successful outcome. The denominator is still going to remain the total number of outcomes, which is 16, representing the total number of tiles that we find on our spinner. Thus, the probability of the spinner landing on a blue tile is calculated as 5 over 16, also translated to 31.25%. While 31.25% might still be considered not highly probable, it's significantly more likely that we're going to land on a blue tile than we were to land on one specific number with our spinner. Hang tight with me as we're going to work through this probability question. I promise we're going to get through it. The question states, a bag contains 5 red marbles, 3 blue marbles, and 2 green marbles. If 2 marbles are drawn one at a time from the bag at random without replacement, what is the probability that both marbles drawn are going to be red? So we're looking for red marbles. We know that we're drawing marbles one at a time from the bag at random and we're not replacing them without replacement. So we start off by asking ourselves, how many marbles do we have? Because based on probability, our equation is going to be the number of favorable outcomes, that's our top number, our numerator, and underneath that it's going to be the total possible number of outcomes. So that's what we're going to figure out first, the total possible number of outcomes. So we know that we have 5 red marbles, we have 3 blue marbles, and we have 2 green marbles. So if we add all of these together, we know that we have a total of 10 marbles. So we know that the denominator of our equation is going to be 10, okay? So now we need to figure out what we're drawing each time we draw. We know that we have 5 red marbles. So the possibility of us getting one of those red marbles is going to be 5 out of 10. 5 is our number of favorable outcomes because we have 5 red marbles, and 10 is a total number of possibilities that can occur because we have 10 marbles in the bag. So say we pulled out a red marble the first time, we're not going to replace it, right? Without replacement. That's what it states. So now how many marbles do we have in the bag? Well, now we have 9, right? So now our denominator is going to be 9 because we have only 9 possible outcomes since we've already drawn one of the red marbles. Well, we've already drawn one of the red marbles. How many red marbles do we now have in the bag? 5 minus 1 is equal to 4. So our next fraction is going to be 4 out of 9. There's 4 number of favorable outcomes because we have 4 red marbles left. And we have 9 total number of possible outcomes because we only have 9 marbles left. So based on our 2 drawings, our first should be 5 out of 10 and our second should be 4 out of 9. Now we are going to multiply these 2 possibilities together. Okay, so we know that we have 5 out of 10. We are going to multiply that by 4 over 9 because we have the word and. So whenever we are looking for 2 things together, we use the word and. That means we are going to multiply our outcomes. Something very important that you're going to have to know for the T's is when we are looking for 2 outcomes together, we use usually the word and. And anytime we have the word and, we're going to multiply the outcomes together because we're going to have 2 outcomes that we're going to need to know together. Whereas if you start to see the word either or, we are going to add the outcomes together. So anytime that you are trying to figure out two things, like and, in this case, we're trying to figure out the probability of both marbles, right? And two marbles, we are going to multiply outcomes. Whereas if it was asking or, whether we were going to get a red or a blue, then we would add the outcomes together. So very important when you are taking your TEAS exam. So in this particular case, we are trying to figure out both marbles, right? That's our and. So we are going to multiply. So we are going to multiply our top together. 5 times 4 is equal to 20. And we're going to multiply our denominators together. So 9 times 10 is equal to 90. But if we take a look at our examples here for our answers, we don't have anything that says 20 over 90, right? We're going to have to simplify our fraction. You can either do the math if you want to, but what I do is I just remove the corresponding zeros from the end of each equation. It just makes it a lot easier. And that is going to give me 2 over 9. So the probability that we are going to pull a red marble both times without replacement is going to be 2 over 9. Do we have that? Yes, we absolutely do. The correct answer is going to be B, 2 over 9. The ATI TEAS is going to test you on different graphical display types and how you use them. There are 5 different types of displays that you're going to encounter when you take your TEAS. One is the Cartesian coordinate, scatter plot, line, pi or circle, and bar graphs. Let's break each one of these down. Starting with Cartesian coordinate chart, also known as Cartesian graph, consists of 2 perpendicular lines or axes. The horizontal axis is called the x-axis and the vertical one is called the y-axis. Their intersection at 0 creates an origin, which is the starting point of plotting data. As an example, let's look at how we would plot 5, 4. So starting at our origin, 0, 0, right here in the middle, if you look to the left and right of the origin point, you're going to see that you have negative numbers that move towards the left, and you're going to have positive numbers that move towards the right. It's very similar if you're looking at a number line. In our example 5, 4, the first data point is a positive number, so we would move to the right 5 spaces on our x-axis. When you're looking at our y-axis, we can see that the origin point 0, 0 has kind of the same thing like we saw with our number lines in our x-axis. So as we move up our number line, it becomes more positive, and as we move down our number line, we become more negative. Our next data point is a positive number, so we're going to move up 4 spaces to get to 4. Now we're just going to place a dot at this position of our plot, and that is our point, 5, 4 on our Cartesian coordinate chart. Not too bad, right? Next, let's look at scatter plots. So this type of graph is essential when we want to examine relationships between 2 different data sets or numerical variables. Essentially, it's about observing how one variable correlates to the other. Let's consider the example of our scatter plot found here on the right side of your screen. It investigates the amount of ice cream sales dependent on environmental temperatures. As you can see, over time, the hotter the temperature outside becomes, the more sales of ice cream increase. Scatter plots do hold significant value in scientific studies. They are particularly useful when we need to alter one variable, known as our independent variable, and observe its impact on the other, called our dependent variable. When we're setting up our scatter plot, it's crucial that we place that independent variable on our x-axis. This would be our x. For instance, if you're conducting an experiment where you vary the amount of fertilizer given to a plant to measure its growth over time, the amount of fertilizer, our independent variable, would go on the x-axis. The growth of our plant, the dependent variable, would be along our y-axis. By doing it this way, you can effectively analyze the correlation between these 2 factors. As you can see, the amount of fertilizer increases the growth of the plant. Now let's look at a line graph. So a line graph is ideal in observing changes over time. So take, for instance, examining the produce sales over 9 months. In this scenario, the timeline is plotted along our x-axis, showing us the individual months while the financial values are marked on our y-axis, showing the sales in the thousands. In a scientific context, we may be studying the respirations of a nursing student during clinical checkoff. A line graph proves invaluable for this information. If you're measuring how much oxygen the nursing student consumes over a period of time from just going into check-in, during, and then after, a line graph will notice and illustrate these changes over time. This makes it a perfect tool for visualizing and analyzing data that varies with time. This is probably one of the most familiar charts, and this is a pie or circle chart. They use both names interchangeably. As you can see from our pie chart that we have here as our example, there was a survey that was completed in 2020 for nurses who were leaving a facility. The data collectors collected information based on their reasons for departure, and these were the results. As you can see from our pie chart, each color corresponds to a different reason. So for example, people leaving for personal reasons was about 50%. Those who transitioned to a competitor was about 20%. Travel nursing was about 13%. No opportunity to advance was 10%. And then lastly, those individuals who did not provide a reason was 7%. A bar graph is particularly useful when we need to compare multiple groups or categories. For example, in our first set of bar graphs, you can see that it illustrates the number of worldwide electric cars per year. As you can see, as the years progress, the number of electric cars also increase. Going back to our plant experiment that we talked about before, imagine that we're in a laboratory setting, investigating how various light colors affect the rate of photosynthesis. In such a case, a bar graph would be an excellent choice for this experiment. We could plot the rate of photosynthesis here on our y-axis, with each color represented as a distinct bar down here on our x-axis. Often in bar graphs, each bar signifies the average or mean derived from the collected data. This makes bar graphs a useful tool, and a very powerful tool at that, for visualizing representations of comparing average values across different categories or groups. Here's a quick and useful tool as to why we would use different graphical displays and what specific cases we would use them as. It's a little cheat sheet to help you pass your ATI TEAS when you come across these questions on the exam. All right. Once we've determined the graph to use, we can begin the graphing process. Let's experiment with this concept using hypothetical data from an ice cream sales that we discussed earlier. Imagine that we have data showing the average temperature in an area and the corresponding ice cream cone sales during different months. If we want to illustrate the total ice cream sales in each month as a proportion of the year's total sales, a pie chart would be ideal. Each slice of the pie chart would represent a different month, showing us its average sales that they share over that year. On the other hand, if our focus is tracking the average high temperatures in an area over time, a line graph would be the way to go. This graph would effectively depict temperature trends throughout the year. Now let's say that we're interested in comparing ice cream sales across specific months. In this scenario, a bar graph would be highly effective. It would allow us to compare the ice cream sales to the specific months side by side, providing a clear visualization of the comparison. Let's dive into the practical creation and interpretation of graphical displays. This is very important for you to know for the TEAS, and we're going to start by focusing on scatter plots. Using our previous data set, here is how we would construct the scatter plot and what each element represents. The very first thing that we want to do is we want to establish our axes. So on the x-axis, we're going to plot the average high temperatures, and on the y-axis, we're going to plot our ice cream sales. It's important that you make sure that you label each axis clearly, including the unit of measures that you're using. For instance, the x-axis might be labeled average high temperature, and we're using the unit of measure of Fahrenheit. And on the y-axis, it is our ice cream sales, and we're doing cones per month. We also want to make sure that we title our graph. A good title should encapsulate the essence of the graph's content. It's not enough to just have a vague title like ice cream, right? Instead, it should be informative, such as Correlation of Ice Cream Sales and Average High Temperatures 2023. This title should essentially narrate the story of the data that we're trying to present. After labeling our chart, we can now plot the data points. In a scatter plot, each point represents a data pair correlating between temperature with sales. The arrangement of these points can reveal patterns or correlations. An important feature of our scatter plot is our best fit line. This line represents the average trend through our data points. When drawing it freehand, we aim to position it so that roughly half the points lie above it and the other half lie below it. Remember, this line should not go beyond our range of data as it represents interpolation within the existing data set. Avoid putting any kind of arrows or extending them past the outermost data points. In addition, in terms of scaling, we want to ensure that the increments of each axis is uniform and clear. For instance, if each major grid line of the x-axis represents an increment increase of 15 degrees Celsius, this should be consistently applied throughout our line. In our case, with this graph, the ice cream sales and average temperature increase in increments of 10. Lastly, remember that including 0 on your graph is not always necessary. If your data doesn't include or approach 0, it does not need to be present on your graph. This helps keep the focus on the relevant data ranges and avoids misleading representations. One of the things that the TEAS loves to test you on is bad graphs and misrepresentations. What are we missing? What could be better about our graphs? Let's take a look at the example of a bad graph, focusing on one that's supposed to show how different amounts of fertilizers affect plant growth. When you look at this, you immediately notice several errors. Firstly, the title of the graph, while it is present, isn't descriptive enough. It needs to clearly indicate what is being plotted on our x and y axes, such as the relationship of fertilizer to plant growth. Next, there's a major issue with how the axes are set up. Plant height is actually listed down here on our x-axis, but since we have varying amounts of fertilizer, that actually should be our independent variable and should be placed down here on our x-axis. And that plant height should be moved to our y-axis because it is our dependent variable. It's also crucial to include units for each variable, but as you can see, they're missing here. Plant height should be labeled on the y-axis with appropriate units, and fertilizer amounts should also be labeled on the x-axis with its amounts of units. The scaling of these axes is another problem. The x-axis shows non-linear scaling numbers of 5, 12, 15, 19, 23, and 30. In a well-made graph, the distance between each point should be consistent, uniform, and clear. Additionally, only having a single number on our y-axis, 13, doesn't help with accurate measurements either. Lastly, our best fit line on this scatter plot extends past our range of data. This is also going to be incorrect. That best fit line should only encompass the range of data points on our graph. In summary, the graph has quite a few significant errors, demonstrating what to avoid when creating or interpreting a scatter plot. Let's take a look at our first practice question. Which of the following descriptions best matches a scatter plot? Is it A, a graph that uses vertical or horizontal bars to show comparisons among categories? B, a graph that displays data points along a line typically used to show changes over time? C, a circular graph divided into slices to illustrate numerical proportions? Or is it D, a graph that displays data points to represent the relationship between two variables? And the correct answer is D, a graph that displays data points to represent the relationship between two variables. As we know, a scatter plot is characterized by its use of data points plotted on a Cartesian coordinate system, showing how one variable is affected by the other, which is why D is the most correct answer. You were tasked with presenting the monthly sales data for 3 different products over the course of a year. Which type of graph would be the most effective in displaying this information? Is it A, a pie chart, B, a line graph, C, a scatter plot, or D, a Cartesian coordinate? And the correct answer is B, a line graph. As we know, a line graph is ideal for showing changes over time, making it the best choice for presenting sales data across different months. It allows the audience to easily see trends and compare the performance of the 3 products throughout the year. Pie charts are more suited for showing parts of a whole at a single point in time. Scatter plots are used to show relationships between 2 variables, and Cartesian coordinates would not be used in this scenario. A bar graph is used to compare the average test scores of 4 different classes: algebra, biology, chemistry, and English. Sounds like the TEAS test, right? However, the bars are not labeled with the names of the classes. How does this affect the interpretation of the graph? Is it A, it allows for a straightforward comparison of the test scores across subjects? B, it does not impact the interpretation as long as the scores are visible? C, it creates ambiguity, making it difficult to attribute the correct scores to each class? Or is it D, it improves the visual simplicity of the graph, focusing attention solely on the numerical scores? And the correct answer is C. It creates ambiguity, making it difficult to attribute the scores for each class. Without these labels indicating which bar represents which classes, it becomes impossible to determine the average test scores for each individual class of algebra, biology, chemistry, and English. Now let's talk about linear, exponential, and quadratic graphical trends. In order to understand these three different kinds of trends, we're going to put our imagination hats on. So let's say that we're scientists who are observing turtle populations in a series of islands, focusing first on two islands, Funky Island and Get Down Island. In what we term turtle, euro, zero, 3 turtles each make their way to Funky and Get Down Islands. Upon visiting each island after 1 year, we note that Funky Island's turtle count has risen to 5, while Get Down Island's has reached 6. The following years, F's population, which is our Funky Island, has grown to 7, and our G Island, which is Get Down Island, has impressively doubled to 12. Year after year, we meticulously record our findings, aiming to discern any emerging patterns. We ponder whether the turtle populations expand at a steady pace, a concept known in mathematics as constant difference. Let's take a closer look at each one of these different kinds of islands and graph trends. So starting with Funky Island, we started with 3 turtles. If 2 more arrived each subsequent year, then after a decade, the calculation for Island F would be the initial 3 turtles plus 2 turtles for each of the 10 years, totaling 23. As we generalize this, if X equals the total number of years elapsed, the turtle population on Island F would be represented as 2x plus 3, which intriguingly forms a linear equation, y equals mx plus b, where m is the constant rate of increase and b is the starting number of the turtles. Upon graphing this relationship of Funky Island, we discover a linear trend affirming our hypothesis. This linear model is characterized by a constant increase or decrease. Turning our attention to the turtles on Get Funky Island G, it's another intriguing pattern that emerges. Their numbers seem to double each year, indicating exponential growth rather than linear growth. Unlike that steady addition that seemed to take place on Funky Island, Get Down Island's turtles increase by a factor of 2 annually. To illustrate the population for the 7th year, we would be calculating that by taking the initial 3 turtles and doubling them 7 times, a process conveniently expressed using an exponent. This kind of a pattern aligns with exponential function, which is y equals a times b with the exponent of x, where it represents the starting numbers of turtles, b, as the growth rate, in this case 2, and x is the number of years. Our analysis is confirmed as depicted in the graph of Get Down Island's turtle population. As you can see, we have a nice curve steadily increasing over time. Our findings highlight a fundamental principle of growth patterns. Given enough time, any exponential function with a growth multiplier greater than 1 will surpass a linear function. Lastly, let's focus our efforts on Quick Step Island. Initially, there was only 1 turtle, but by year 1, the count reached 13. By the 2nd year, the number soared to 45, and by the 3rd year, it stood at 97. These patterns present a curious pattern that seems to correlate with the passing of years. The turtle population on Quick Step Island can be described by the formula y equals 10x squared plus 2x plus 1, where x represents the number of years. This means that for the 9th year, the population would be 10 times 9 years squared plus 9 times 2 plus 1. Doing our calculations, we have 9 squared is equal to 81. 10 times 9 is equal to 810. 2 times 9 is equal to 18. And then, of course, we bring up the number 1. So if we add all of these numbers together, we're going to get a total of 829 turtles by the time that we reach our 9th year. This pattern is indicative of a quadratic function, which takes the form of y is equal to a times x squared plus bx plus c. In this case, b is equal to 2 and c is equal to 1. The graph of this function reveals that classic U-shaped curve that's also symmetrical and distinctive when we're looking at quadratic equations. When complementing which turtle population would outgrow the others over time, it might be tempting to say that the quadratic growth of Quickstep Island would be the given choice given its rapid ascent. However, it's important to remember that exponential growth, when it comes to capacity, is going to increase indefinitely and will eventually surpass that quadratic growth. The quadratic function's growth is tethered to the square of x, whereas the exponential growth x serves as the exponent itself, offering boundless potential for increase. Let's take a look at how this will be displayed on the ATI TEAS. Starting with our first practice question. Calvin is selling apples for $2 each at a farmer's market. He has written down his sales for the last 30 minutes as follows. And as you can see over here on the right-hand side of our screen, this is our data points. What type of relationship is depicted between the numbers of the apples bought and the total cost? Is it A, linear, B, exponential, C, quadratic, or D, cubic? And the correct answer is A, linear. The cost increases by a constant amount of $2, with each additional apple indicating a constant rate change. This consistent increment is characteristic of a linear equation where the graph is going to be a straight line. Julie is growing bacteria collected by a bacterial sputum sample for a patient admitted with pneumonia. She documents her findings every hour. What type of graph best represents the relationship between the time and the number of bacteria? Is it A, linear, B, exponential, C, quadratic, or D, cubic? And the correct answer is B, exponential. The number of bacteria doubles with each passing hour, indicating the bacteria count is not increasing by a fixed amount, but rather a fixed proportion. This pattern of growth, where the rate of increase becomes progressively more rapid, is indicative of an exponential relationship. Next, let's take a closer look at directions of trends in graphs. When we're analyzing graphs, it's important to understand that different trends can depict either increasing, decreasing, or no change trends. When we're looking at graph trends, we want to look from left to right. Where does the line start on the left, and what is the trend when we move across to the right? Let's start with increasing trends. So graphs with increasing trends show values that rise as you move from left to right. As you can see from our two different examples, if you look at the starting point on the left, you can see that each line increases in value as we start moving to the right. So as you can see here, we start moving up in value, and again on this example we also move up in our value. So we're going to get a concave up or concave down increasing kind of distribution. With decreasing trending graphs, they depict values that fall as they progress from left to right on the graph. So as you can see from our example, as you look at the starting point on the left, you're going to see that each line is going to decrease in value as we move to the right. So up here we have a concave up decreasing graph, meaning that we start high and then we come down low. And then over here on the right, we have a concave down decreasing graph, again starting high, and as we move to the right, we lower the number. Lastly, we have a no change trends kind of graph. So these graphs will show a flat line representation of a situation where there's no change over time. The value remains constant regardless of the changes that are happening along the horizontal axis. As you can see here, we just have this flat line on our graph, which shows that as we move left to right, there is no change, making it a no change graph. Outliers on graphs are data points that stand apart from the crowd, catching your eye because they don't quite fit in with the rest. Imagine that you're looking at a graph, and while most of the data points are in a cozy cluster, like we see in the graph here on our screen, there's one point or maybe even 2 points that are going to kind of miss the memo with the rest of our data points. They're going to be sitting off far to the side, above or below our best fit line, as you can see here in our example. Sometimes these outliers are a result of a simple slip slip up, maybe a typo or data that was entered incorrectly, or even a glitch in the measurement equipment that we're using. Other times, these are real deal, genuine deviations that tell a story of their own, like a sudden spike in sales after a viral marketing campaign, or an unexpected drop in temperatures on an otherwise warm month. If any of you live in Florida, you know exactly what I mean. These types of questions on the T's tend to be easier because we can visually see the data points and can easily denote that something is wrong. We introduced dependent and independent variables a little bit earlier, but now we're going to dive a little bit deeper into understanding what they mean. The independent variable is often seen as the cause. It's the variable that we manipulate or change to observe how it affects another quantity. On the other hand, the dependent variable is considered the effect. It's the value that depends on or is determined by the changes of our independent variable. For instance, in an experiment measuring the growth of plants based on the varying amount of water, the amount of water given, that is going to be our independent variable, is going to directly influence the growth, our dependent variable. So let's start with the basics when it comes to graphing these variables. The independent variable, which is often plotted on our x-axis, as we know, is the variable that we change in order to control an experiment. Think of it as the input of our cause and effect relationship. On the flip side, we have our dependent variable, which is represented here on our y-axis. And this is the outcome or the effect that we are going to observe as a result of the changes to our independent variable. So essentially, the value of the dependent variable is going to hinge on the influence of our independent variable. If you're trying to figure out how independent and dependent variables affect an equation, it'll look something similar to this. We have the equation y equals 3x plus 5. Based on our equation, we know that y is going to equal the outcome of the value because it is the lone variable on the other side of our equal sign. That means that x is going to be our independent variable. We have control over what we're going to put in x, which is ultimately going to influence our y. Let's take a look at another example. Imagine a hospital system is conducting an experiment to understand the relationship between nurse-to-patient ratios and average recovery time for patients on an orthopedic unit. The task is to represent the given data on a graph. This scenario poses an interesting question. Between the nurse-to-patient ratio and the average recovery time, which is our dependent variable and which is our independent variable? Let's recall that our dependent variable is ultimately going to be influenced by our independent variable. So in our case, does the nurse-to-patient ratio depend on the recovery time, or is it the other way around? Given that in this experiment, we can choose the nurse-to-patient ratio, it implies that the ratio is the variable within our control. Hence, nurse-to-patient ratio is going to be our independent variable, which we are going to plot down here on our x-axis. On the other hand, the average recovery time, which we aim to measure, naturally is going to become our dependent variable, which we're going to plot over here on our y-axis. As you can see down here on our graph, the higher the nurse-to-patient ratio is ultimately going to increase the average recovery time for our patients. Lastly, to test our knowledge from before, what kind of relationship do we see when we're looking at these two variables? Is it linear, exponential, or quadratic? That's right, you've guessed it, it's linear because we have a straight line. Good job! In a study examining the effects of study hours on test scores, researchers tracked the number of hours spent studying X and the results testing scores Y. Given the relationship described in the equation of y equals 2x plus 70, where y represents the test scores and x represents study hours, determine which variable is independent and which is dependent. Is it A, x is dependent variable because it relies on the test scores? B, y is the independent variable because it is determined by the number of study hours? Is it C, x is the independent variable because it represents the controlled amount of study time influencing the test scores? Or is it D, y is a dependent variable because it dictates the number of study hours needed to achieve a certain score? And our correct answer is C. In this context, the number of study hours, which is X, is the variable that the researchers control or manipulate to observe the effect on another variable, making it our independent variable. The test scores, which would be our Y, on the other hand, are affected by the changes in our study hours, making them the dependent variable. The equation Y equals 2X plus 70 clearly shows that Y, which is our test scores, is going to change in response to X, which is our study hours, underscoring the dependency of test scores in the amount of time spent studying. In a clinical trial to assess the effectiveness of a new dietary supplement on improving blood pressure levels, participants' baseline blood pressure readings are taken before starting a supplemental regimen, and their daily supplemental dosage varies among participants. Based on the information provided, which variable is independent and which is dependent? Is it A, medication dosing is the dependent variable because it is influenced by the changes in blood pressure readings? Is it B, blood pressure readings is the independent variable because they determine the dosage of dietary supplement? Is it C, medication dosing is the dependent variable because it represents the dosage of the supplement, which is manipulated to observe its effect on blood pressure? Or is it D, blood pressure readings are the dependent variable because it depends on the dosage of the dietary supplement? And the correct answer is D. In this clinical trial, the variable the researchers actively manipulate is the dosage of that dietary supplement given to the participants, making that medication dosing our independent variable. The purpose of varying that dosage is to observe its impact on a specific outcome, which is, in this case, is going to be our blood pressure readings, making that our dependent variable. Next, let's talk about correlation and covariance. So correlation and covariance is a statistical measure that describes the relationship between two variables. Like in all of our examples for mathematics, we call these variables X and Y. To illustrate this, let's imagine that we plot points on a graph using X and Y axes, and the pattern emerges somewhat like we see in our examples. The way that is depicted in our first example here suggests that positive correlation between X and Y, that is that when X goes up, Y is also going to trend up as well. Now let's also consider a scenario where the inverse relationship is true, like we see in our second example with negative correlation. As X increases, Y is actually going to decrease, causing an inverse relationship. In our last example, we have no correlation, meaning that the points are plotted on the X and Y axes, but they don't follow the same trend or have any correlation. As you can see from our graph, we're unable to draw any kind of line through any of these plotted points to show a relationship among them. This shows that there is no relationship between these points as they're scattered all throughout our graph. A study was conducted to explore the relationship between a number of hours spent studying per week and the resulting GPA of college students. The data collected from a sample of students is presented in our table that we have right here on the right-hand side of our screen. Based on the data provided, what kind of correlation exists between the number of hours studied per week and the GPA? Is it a positive correlation, A, B, a negative correlation, C, no correlation, or D, cannot be determined from the data provided? And the correct answer is A, we have a positive correlation. The table shows that the number of hours studied per week, which is our X, increases, and the GPA, which is our Y, also increases. This upward trend suggests that we have a positive correlation, indicating that students who spend more time studying tend to have higher GPAs. So this next question can tend to be a little bit tricky, so hang tight with me. A fitness coach is analyzing the relationship between the number of calories consumed daily, that's our X, and the weight change Y in kilograms observed over a month in clients. The following data is recorded in a table. What does the data suggest about the covariance between daily caloric intake and weight change? Do we have a positive covariance, A, negative covariance, B, C, zero covariance, or D, the data is insufficient to determine covariance? And the correct answer is B, we have a negative covariance. So the table illustrates that as the daily calorie intake X increases, the number change Y shift decreases. This pattern implies that the negative covariance between caloric intake and weight change indicates that a lower calorie intake is associated with less weight gain and more weight loss. Lastly, we're going to highlight the concept of proportionality, which fundamentally comes in two flavors: direct and inverse proportionality. Let's start with direct proportionality. In this scenario, we use variables y and x, like we have always so far, to describe a situation where y increases or decreases in tandem with x. Mathematically, we express this relationship as y is equal to kx, where k represents proportionality constant. This constant of k is crucial as it determines the specific relationship between y and x, ensuring that any change in y is going to be directly linked to the proportional change in x. So what does this mean in real-world scenarios? So if you consider the relationship between the distance by a car and the time it takes to travel, that distance is a constant speed. As the time increases, the distance traveled also is going to increase. If a car is traveling at a steady rate of 60 miles per hour, the distance covered is directly proportional to the time traveled. Now let's pivot a little bit to talk about inverse proportionality. In contrast to direct proportionality, when we say that y is inversely proportional to x, we're describing a situation where as y increases, x is going to decrease and vice versa. The mathematical representation for indirect or inverse proportionality relationships is y is equal to k over x, where k remains our proportionality constant. However, in this formula, k is positioned above x and a fraction, signifying the inverse relationship. This setup implies that x, as it becomes larger, y is going to get smaller, and the opposite of true when x decreases. A real-world example of this is a relationship between the amount of time taken to complete a task and the amount of workers assigned to that task. If more workers are assigned to that task, the time taken to complete the task is going to decrease. And if fewer workers are assigned to that task, then the time taken is going to increase. This is a great example of inverse variation, where the increase in the number of workers tends to decrease the amount of time that it takes to complete a task. Graphs representing direct and inverse relationships exhibit distinct characteristics based on the nature of the relationship between the two variables. As we discussed, in a direct relationship, as one variable increases, the other variable is going to increase at a constant rate. This is reflected in our graph as a straight line. If you plot y, our dependent variable, against x, our independent variable, for a direct relationship, y is equal to k times x, the line will pass through the origin 0, 0. The slope of this line is determined by that constant k, and the line will ascend to the right if k is positive, indicating that y increases and x is also going to increase. In an inverse relationship, as one variable decreases, the other variable is going to increase. This type of relationship is captured by our equation like we talked about before, is y is equal to k over x. And the graph is going to look significantly different from a direct relationship graph. Instead of seeing that straight line that we've become accustomed to, the graph is actually going to feature a curved line that approaches the axes but is actually never going to touch them. As x increases, the y value is going to decrease, approaching 0 but never actually reaching it, reflecting that inverse relationship between the two variables. A biology experiment investigates the growth of a plant species under different light intensities. The table below shows the height of the plant's y after 30 days of various light intensities x. Based on the data provided, which statement best describes the relationship between light intensity and plant height? Is it A, as light intensity increases, plant height decreases, indicating an inverse relationship? Is it B, there is no clear relationship between light intensity and plant height? Is it C, as light intensity increases, plant height increases at a constant rate, suggesting a direct relationship? Or is it D, Plant height changes unpredictably with changes of light intensity. And the correct answer is C. The table shows a consistent pattern where we double the light intensity is going to result in doubling that plant's height. This proportional increase indicates a direct relationship where the plant height is directly proportional to our light intensity. A physics study examines the cooling time of a hot beverage as a function of the amount of cream that was added. The table shows the cooling time Y for the beverage to reach a drinkable temperature for various amounts of cream added, X. What does the data suggest the relationship between the amount of cream added and the cooling time of the beverage? Is it A, adding more cream significantly increases the cooling time, showing a direct relationship? Is it B, the cooling time decreases as more cream is added, illustrating an inverse relationship? Is it C, there's no significant change in cooling time with varying amounts of cream, indicating no relationship? Or is it D, the relationship between the amount of cream added and the cooling time is inconsistent? And the correct answer is B. The data indicates that as the volume of cream increases, the cooling time of the beverage to reach drinkable temperature decreases. This temperature suggests that the cooling time is inversely related to the amount of cream that's added, as an increase in one leads to a decrease in the other. Let's start off by exploring the concepts of perimeter, area, and volume as a whole. To quantify a one-dimensional object, we use a one-dimensional measure known as length. For instance, the length of a given line might be precisely 1 centimeter, a standard unit of measure when it comes to length. If we take that same line and we extend it perpendicularly by 1 centimeter, this is going to transform into a two-dimensional shape, specifically a square. Two-dimensional shapes are quantified by a two-dimensional measure referred to as area. Since our initial line of 1 centimeter in length was extended by 1 centimeter to the right, the resulting square covers an area of 1 square centimeter, a typical unit of measure when we are trying to figure out area. Now let's consider extending that two-dimensional shape up from its plane of 1 centimeter. This new action creates a three-dimensional shape known as a cube. To quantify a three-dimensional object such as this, we're going to utilize the three-dimensional measure known as volume. When we talk about volume, we're quantifying the amount of three-dimensional space inside our object in which it fills. So what is the volume of a cube? Given that our volume of cube was formed by extending a square centimeter up into a third-dimensional shape by 1 centimeter, the volume of this cube is defined as 1 cubic centimeter, a standard unit of measure when we are measuring volume. To make it easier, area is measured as square units and volume in cubic units. Square units results from multiplying two one-dimensional units, centimeter times centimeter, often expressed in exponent notation as centimeters squared or centimeters raised to the second power. Conversely, cubic units arise from the product of three one-dimensional units, centimeter times centimeter times centimeter. This is abbreviated in its exponent notation as centimeters cubed or centimeters raised to the third power. Let's break each one of these three concepts down further and apply them based on the guidelines of the TEAS. So let's start by diving into the fundamentals of geometry when it comes to perimeter. It refers to the total distance or length around a shape. Now, you might wonder, what does it mean to measure the distance around a shape? Well, distance or length is the concept that exists in one dimension. It is quantifiable in units such as centimeters, inches, or miles. This means that perimeter is also a one-dimensional measure, quantified with units of length. So when we talk about a shape's perimeter, we're not just saying 10, we're saying 10 centimeters. Or it's not just 25, it's 25 miles. The specificity of units is crucial when we're discussing perimeter. But then, what do you mean by around a shape? What we mean by this is it's the absolute shortest path around a shape. This is the distance that you cover if you were to trace a line around the shape's border or its edge. A helpful way to understand perimeter is to imagine yourself walking along the edge of a shape, such as this pentagon. Visualize yourself beginning at one end of the pentagon and walking all along the edge of the shape until you reach back to your starting point. That complete distance that you cover is equal to the perimeter of the shape. In our example, we know that every side of the pentagon measures 10 meters. Transversing all 5 sides of this shape is going to equal a total distance of 50 meters. Another insightful method to grasp the concept of perimeter is to imagine taking the shape like our pentagon and separating it from its corners. You could unfold that shape into a straight line. That length from the start of your line to the end of your line is your perimeter. Calculating the perimeter of polygons, which are shapes that only have straight edges, is pretty straightforward. You simply sum the lengths of all the sides, and the result of the polygon is the perimeter. Let's practice some examples of how this actually works. We're going to start with a right triangle. The triangle sides are 3 centimeters, 4 centimeters, and 5 centimeters. To determine the triangle's perimeter, we need to add the lengths of each individual side. So we calculate 3 plus 4 plus 5. Total gives us 12 centimeters, and that is our right triangle's perimeter. In our next example, we have a hexagon, a polygon with 6 equal sides. This hexagon is described as regular, meaning that every single side is the exact same length. This actually simplifies our task because only one side's length is actually given to us, which is 4 centimeters. We can infer that every single side along this hexagon is going to be 4 centimeters long. Instead of adding each side individually as we did in our previous example, we can actually take a shortcut and use multiplication, since all the sides are of equal length. That's because multiplication is really just repeated addition. To find the total perimeter, we would simply multiply the number of sides, that would be 6, by our length of the one side that we know, which is 4 centimeters. 4 times 6 is going to give us 24 centimeters, which is the overall perimeter of our hexagon. Let's do a more complicated example. This time we're looking at a polygon with 6 sides again, but this one isn't regular. That means that the lengths of each side is going to vary. This example is a bit more challenging because the diagram only reveals the lengths of 4 sides, leaving us with 2 sides that are unknown. Encountering incomplete information is very common in mathematics and also on the TEAS. The strategy here is to leverage the information that we do have to deduce the information that we're missing. Here's how we're going to approach this. Pay attention to the 2 vertical sides that we have here on our screen. 4 inches and 6 inches. Now imagine that you could slide these 2 vertical sides across the opposite side, and both of those sides are going to equal the length of that missing side. So as we know, we have 4 and we have 6, so when you add these together, we actually get a total of 10. We can apply this similar logic to our horizontal sides as well by shifting these lengths that we have available to us of 10 inches and 5 inches. So if we slide those down, we have 10 and we have 5. We're going to add those 2 totals together in order to get the horizontal side that we're missing. So our missing side is 15 inches. By utilizing the lengths we knew, we managed to deduce the lengths that were unknown to us. With the knowledge in hand of every side's length, now we can actually calculate our perimeter. So 10, which is our number up here, plus 4, plus 5, plus 6, plus 15, plus 10 gives us a total of 50 inches, which is the perimeter of our irregular polygon. Now let's step it up a notch by talking about how we calculate circumference and area of circles. It's crucial that you familiarize yourself with the formulas for both of these, as they are going to be fundamentally covered when it comes to the TEAS. The formula to calculate circumference of a circle is going to be circumference is equal to pi multiplied by the diameter. In shorthand, we have C is equal to pi times D, where C is our circumference and D is our diameter. So you might be asking yourself, what the heck is a diameter, right? So if we were to take a circle and we were to draw a line through the center of that circle, that line from one end of the circle to the other end of the circle, that measurement is considered our diameter. An easy sentence to remember this equation is cherry pie's delicious, where C in our cherry is equal to our circumference, pi is of course equal to pi, and the D in delicious is equal to diameter. Now how do we calculate a circle's area? So the area, which is the region enclosed within our circle's boundaries, is area equals pi multiplied by radius squared. So what exactly is a radius? So our radius is actually half of our diameter. So as we know, we drew a line down the center of our circle in order to get a diameter. We're just going to take the diameter and divide it by the number 2 in order to get our radius, which is half the diameter. An easy sentence to remember this equation is apple pies are 2, where the A in apple is our area, the pi is of course our pi, the r in our r is our radius, and the 2 is going to be the square of our equation. A crucial point to remember is that r squared does not mean 2 times r. This is frequently misunderstood among TEAS test takers who first learn to calculate area of a circle. When we're examining both formulas closely, their similarities become apparent. Each formula involves multiplying pi by a specific circle measurement to determine either circumference or area. For circumference, the calculation involves pi multiplied by the diameter, while for circle, it's pi multiplied by the radius squared. How do we distinguish between a diameter and a radius? Well, as we know, the diameter is the line that we draw across the center of a circle that divides a circle into 2 equal halves. That line measurement from one end of the circle to the other end of the circle is our diameter. Sometimes the TEAS is going to give you questions that's only going to give you the radius. Well, in order for us to figure out the diameter based on the radius is we're going to take the radius and multiply it by 2, because 2 times the radius is going to give us the full length of our diameter. So when we're talking about area, we're going to do something a little bit different when it comes to our radius. We're going to actually square our radius. And when we talk about squaring, it is not the same thing as 2 times r. When we square, we actually multiply the number by itself. So if our radius was 2, 2 times 2 is going to equal 4. If our radius was 5, 5 times 5 is going to equal 25. So that is the big key differences between diameter and radius when we're trying to figure out circumference and area. Let's take a look at an example of how this will actually be applied on the TEAS. So starting with our first example, we're given the exact same circle, and our circle is given us a radius of 8. So when it comes to considering the circumference of a circle, we're actually going to multiply the radius by 2 like we discussed before. So in this case, 2 times 8 is equal to 16. So we're going to plug that into our equation. Pi is just a fancy way of saying 3.14 when it comes to your TEAS. So you can automatically manipulate the pi to be 3.14. So we're going to multiply that by 16, and that is going to give us our circumference of this circle as being 50.24 meters. Next, we're going to figure out the area of the exact same circle. So again, we know that the radius is 8, but instead of multiplying it by 2 like we did in circumference, this time we're going to square it. So 8 times 8 gives us 64 meters squared. We're going to multiply that by pi, which is 3.14, and that is going to give us our total area of 200.96 meters squared. Now that we have a better understanding of one-dimensional values of perimeter and two-dimensional values of area when it comes to a circle, let's explore other shapes when it comes to polygons and area. So to grasp this concept of area, we imagine that that 1 meter line in length is going to be dragged across perpendicularly to create another 1 meter line. When we do this, we create a two-dimensional shape. In this case, it's a square. So when we talk about area, we're trying to figure out the measurement within this shaded region when it comes to our different polygons. So we're going to start by trying to figure out the measurement for 3 shapes: squares, rectangles, and triangles. To determine the area of a square or a rectangle, we simply multiply the dimensions of its side. Typically, we're only measuring 2 sides, which would be our length times our width. So if we have in our first example, we have a square that has 2 sides of 2 centimeters each. So we're going to multiply length times width. 2 times 2 gives us 4 centimeters squared. So the area of this square is equal to 4 centimeters squared. Just like with our square, we're going to use the same formula when it comes to our rectangle. So in this case, we have a length of 4 centimeters and we have a width of 2 centimeters. So we're just going to multiply length times width. 4 times 2 is going to give us 8 centimeters squared, which is going to give us the overall area when we're trying to consider our squares and our rectangles. Now, how do we figure out the area of a triangle? So we're going to begin with a rectangle once more, and this time we have a dimension of 3 centimeters by 4 centimeters. Using our previously discussed formula, the area of a rectangle is calculated as 3 times 4 is equal to 12 square centimeters. Now let's imagine that we're slicing this rectangle in half diagonally from one corner to the opposite corner. This action creates 2 triangles, each occupying half of the area of our original rectangle. Given that the rectangle's area is 12 square centimeters, the area of each triangle would be half of the overall area that we saw in our rectangle, meaning that each triangle is 6 square centimeters. This revelation leads us to the formula for the area of a triangle being essentially half of the area of a rectangle. So instead of area equals length times width, the formula of triangle modifies to area equals 1/2 of length times width. However, there's a slight adjustment that we need to note. For our triangle's dimensions, we actually refer to them as base times height instead of length times width. Here's the reason. The labels length times width are suitable for a right triangle, as a right triangle forms precisely 1/2 of our rectangle. However, these terms don't fit as well with other triangle types, like we see with acute and obtuse triangles, where it's less clear which side should be labeled what. In the case of these triangles, we adopt a different approach. We select one of the 3 sides as our base. The choice of the base is really up to you, and often the base is predetermined in mathematical problems anyways. And once we select that base, we envision placing that triangle on the ground with its base being horizontal. Now we have to figure out what is going to be our height. We do this by finding our triangle's peak, also known as the apex of our triangle. Once we find that, we're going to highlight that and draw a little line down until we hit the base. That is going to be the height of our triangle. In certain cases, such as with acute triangles, the line is going to fall within our triangle's boundaries. But for obtuse triangles, this height line extends outside of our triangle's perimeter. Regardless of its position, the formula to calculate the area of a triangle is going to remain the same consistently. Area equals 1/2 of our base multiplied by our height. Let's take a look at a couple different examples when it comes to triangles. We're going to start off with our acute triangle. So as we know, our acute triangle formula is going to be 1/2 times our base times our height, because as we know, any triangle is basically 1/2 of a rectangle. So we have our base is equal to 5 meters and our height is equal to 8 meters. We're just going to go ahead and plug and play. We've got 5 times 8 is going to be equal to 40 meters squared, of course, because we're dealing with area. And then we are just going to divide that overall number by 2. So the area of our acute triangle is going to be 20 meters squared. Now let's take a look at our obtuse triangle. So again, using the same formula, we have a base of 4 and we have a height of 7. So we're going to plug those numbers into our equation. 4 times 7 is equal to 28 inches squared. And we're just going to take that number and divide it by 2. So the area of our obtuse triangle is equal to 14 inches squared. Now let's talk about parallelograms and trapezoids, because they are most commonly tested on your TEAS. Starting with a parallelogram, it kind of resembles a rectangle, but it lacks those 4 right angles typically that you would see when it comes to our rectangles. To determine a rectangle's area, we typically use the formula area equals length times width. We apply a similar approach when we're looking at parallelograms. So let's imagine taking a segment of our parallelogram and sliding it across to the other side of our shape, fitting it in like the perfect puzzle piece. So if we take down here one part of our parallelogram, which is shaped like a triangle, and then add our triangle here down to the end of our parallelogram, this rearrangement is going to transform our parallelogram into a rectangle without altering its dimensions. Therefore, we can still utilize the formula area equals base times height to calculate the area of our parallelogram following those same principles that we see with our rectangle. So in this example, we have a base of 5 and a height of 2. We're just going to go ahead and plug those numbers into our equation, and that is going to give us the overall area of our parallelogram is 5 times 2 is equal to 10 feet squared. Now, finishing off this area section with a trapezoid, you might have noticed that the formula for calculating this trapezoid bears a remarkable resemblance when it comes to triangles. The area of a triangle can be expressed as base times height divided by 2. However, for a trapezoid, the formula adapts to include both bases. Base 1 plus base 2 times our height is all divided by 2. Let's explore why that is. A trapezoid can effectively be segmented into two triangles by drawing a diagonal line from the bottom of one end to the top of the other end, depicted by the red line that I just drew for you. This division splits the trapezoid into two triangles. The bases of these triangles align with the lengths of the trapezoid's top and bottom edges, and their shared height is identical to the trapezoid's vertical height. In order to find the area of a trapezoid, we could calculate the area of each triangle separately and then sum them up together. But to save ourselves from that frustration, this step can be streamlined by simply adding both bases together, base 1 and base 2, multiplying that outcome by its height, and then dividing it by 2. So taking a look at our example that we have here, we know that we have a base of 8, a base of 4, and our height overall is 6. So we're just going to add our two bases together, multiply it by its height, and divide it by 2. So 8 plus 4 multiplied by 6 gives us 72. And then we're just going to divide that by 2 to give us the overall area of our trapezoid as being area is equal to 36 inches squared. So let's take a look at one more example of a complex shape. So here we have a heart, and we're trying to figure out what the overall area of that heart is. So step 1 is we want to identify the shapes and formulas that we're going to use in order to find the area of our heart. So we have a couple different shapes. We have a square, which is this area that's right here. And then we have a circle formula, which are these areas right here. Step 2 is we're going to start with our easier shape. We're going to start with our square and figure out the area for that. So we know that the square area is length times width. So we have a length of 4 and we also have a width of 4. So we're going to multiply 4 times 4, and that's going to give us the overall area of our square as being 16 centimeters squared. So step 3 is we want to calculate the next shape's formula. So as we know, we have two semicircles along the edges of our square. So we need to figure out what is going to be the area of our semicircles. And all we do is we take our equation when it comes to area of a circle, and then we divide it by 2 in order to get the overall area of a semicircle. So starting with our equation, we have apple pies are 2, which is a is equal to pi r squared. That's how we're going to figure out the area. So in this particular case, we know we have a diameter of 4, and we know that in order for us to determine the radius is we have to divide that diameter by 2. So we're going to divide by 2, and that is going to give us 2 as our radius. So now we just need to plug it in. So a is equal to pi times 2 squared. We know that 2 squared is equal to 4. 4 times 3.14, which is the equation of a pi, is equal to 12.56. Now we need to divide this number by 2 because we don't have a full circle. We only need half the circle. So as we divide by 2, that is going to give us overall area of our semicircle as being 6.28 centimeters squared. And finally, in step 4, we can add all of our areas together. We have our two semicircles, so each one was 6.28. This is semicircle 1, semicircle 2. And then our last shape, number 3, which we know was our square, is equal to 16. If we add 6.28 plus 6.28 plus 16 is going to give us the overall area of our irregular shape as being 28.57 centimeters squared. Now let's talk about volume. As we discussed before, volume quantifies the amount of three-dimensional space an object fills. We create three-dimensional objects by extending a two-dimensional shape up in height from its plane to create a three-dimensional object. Starting with square and rectangle, projecting these shapes into the third dimension yields a three-dimensional figure known as a square prism or cube and a rectangular prism. Similarly, if we extend a triangle into its third dimension, it's going to produce a triangular prism. To determine the volume, you can simply calculate the area of an initial two-dimensional shape and then multiply that by the height in which you projected it. So if you can understand the area when it comes to squares and rectangles, we know that volume is going to be really easy because the only additional thing that we are measuring here is the height. So in this case, we have length times width times height will give us the volume of squares and rectangles. In our example, we have 4 times 3 times 10 is going to give us the overall volume of 120 centimeters cubed. Next, let's calculate the volume of a triangular prism. Just like with the area of the triangle, we multiply half of our base times our height. But again, we've added an additional unit of measure, which is our length in this situation. So if you can remember the area of a triangle, it's going to be really easy for you to remember the area when it comes to a triangular prism, because the only thing that we are adding is that additional unit of measurement, which is our length. So in this case, we have our base, that is 10, and our height, that is 8, length, that is 50. So we are going to multiply 10 by 8 by 50, and we're going to divide that by 2, just like we would do with area. But this time, our volume, using our new equation, is equal to 2,000 inches cubed. Another easy three-dimensional shape to remember the formula for is going to be our cylinder. So again, the base of our cylinder is just a circle. So how do we find the area of a circle? Well, apple pies are 2, right? So area is equal to pi r squared, just like we see here at the beginning of our formula. But because we made this into a three-dimensional shape, we're adding, or I should say multiplying, one additional unit of measurement, and that is our height. So we're going to take the formula that we have for an area of a circle, and we're going to multiply that by its height. So in our example here, we have a radius of 2, so we just plug that into our equation, and we have a height of 10 meters. So 2 squared is equal to 4 meters. 4 times 10 is equal to 40 times pi, which is again 3.14, is going to give us the overall volume of our cylinder as being 125.6 centimeters cubed. So not all volumes are going to extend into a perfect polygon or circle in terms of height. The TEAS is going to test you on 3 additional shapes: cone, rectangular pyramid, and sphere, that are not going to follow all of those same rules. When calculating the volume of a cone and comparing it to a cylinder of identical radius and height, an interesting relationship actually emerges. The cone's volume is precisely 1/3 that of the cylinder. To visualize this, imagine placing a cone inside a cylinder where both the radius and the height are the same. This setup reveals that the cone occupies 1/3 of the cylinder's volume. This phenomenon is why, when determining the volume of a cone, we apply that same formula that we have for a cylinder, but we are going to divide the result by 3. This adjustment to the formula accounts for the cone's proportional volume relative to that of a cylinder. So taking a look at our example, we have volume is equal to pi times r squared times height divided by 3. So we know that our radius is 5 and our height is 12, so we're just going to plug in our numbers. So this is going to give us pi times 5 squared times 12 is divided by 3. 5 squared is equal to 25, and we're going to multiply 25 by 12 times pi, and that is going to give us 300 pi. All we're going to do now is we're going to divide that total number by 3. And that is either going to give us 100 pi or 314 inches cubed. Remember, the TEAS might test you on both of these examples. As with cones, the same concept is also going to apply when it comes to rectangular pyramid shapes. The base of our shape is just a rectangle, and the volume of a rectangle pyramid is precisely 1/3 of a rectangular prism. When we're trying to determine the volume, we apply that same formula for a rectangular prism, and we're going to divide the total outcome by 3. So taking a look at our equation, we have volume is equal to length times width times height divided by 3. We have a length of 8, a width of 7, and a height of 11. So we're just going to plug in our numbers. 8 times 7 is equal to 56, times 11 is equal to 616, and then we're just going to divide that overall outcome by 3, which is going to give us a total volume of 205.33 inches cubed. Now finally we have the volume of a sphere. It's difficult to explain the volume when it comes to a sphere without getting into a whole bunch of calculus and how this formula is determined. To save ourselves some time and frustration, I use the sentence to remember this equation. For spheres, we find the space inside with 4/3 pi times r cubed applied. So looking at our formula, we have volume is equal to 4/3 times pi times r cubed. Remember, anytime that we're dealing with volume when it comes to circle, we're going to cube the radius. Anytime we're dealing with area when it comes to circles, we're going to square the radius. So again, we know that we have a radius of 10 inches. So we're just going to go ahead and start plugging in. So you have 4/3 times pi times 10 cubed. We know that 10 cubed is 1,000. We are going to times that by 4/3, and that is going to give us either two answers depending on how the TEAS lists it. It's either going to be 1,333.3 pi or 4,186.6. Throughout the world, various units of measurements are used across many different countries. However, the most widely adopted system globally is known as the metric system. In fact, there's only 3 countries around the world that don't use the metric system. And guess what? The United States is one of them. Starting with the standard system, also known as the United States customary system, includes units such as length. You're going to see inches, feet, yards, and miles. We've got weight, where we use ounces and pounds. And we have capacity, where we use teaspoon, tablespoon, cups, pints, quarts, and gallons. In comparison, we have the metric system, also known as the International System of Unit, SI. The system is actually decimal based, meaning that it's based on powers of 10, which simplifies calculations and conversions between units. In the metric system, you're going to see length, in which they use the unit of meters. Then we have weight, which is the unit of grams, and we have capacity, which uses the unit of liters. Overall, the metric system is much simpler than the standard system. Understanding both systems, though, is going to be beneficial when you're taking your TEAS, especially in the field of science, as you're going to be using these conversions quite a bit when you enter healthcare. We're going to begin by converting customary units of length, specifically working on feet, inches, yards, and miles. So we have about 8 conversions in front of us that we're going to tackle together, aiming to solidify our understanding of these measurements. So let's get started on our first example. You're going to notice up here at the top of your screen, I gave you like a little cheat sheet of the breakdown of the most commonly seen units of measure conversions when it comes to the standard system that the TEAS is going to test you on. So the first one, as we know, 1 foot is equal to 12 inches. 1 yard is equal to 3 feet or 36 inches, and 1 mile is equal to 1,760 yards or 5,280 feet or 63,360 inches. So let's break down our examples to see what that'll look like on your test. So for this first problem, we need to consider that 1 foot is equal to 12 inches, like we have up here at the top of our screen. So when you think about the length of a ruler, right? A ruler is 12 inches. It's about 1 foot. When we have 2 feet, it's logic that we would follow by just multiplying that 2 feet by 12 inches. So 2 feet times 12 inches is going to give us 24. So the correct answer to this question is 24 inches. So this is a really important concept for you to know. Whenever we're converting from a larger unit like feet to a smaller unit like inches, the operation that we're going to use is multiplication. And if we're going the other way around, where we have a smaller unit going to a bigger unit, we're going to use division. You have to remember this is going to be crucial when you're taking your ATI TEAS and you're navigating between units, because even in the metric system, you're going to use these same principles. So our next example is 48 inches to blank feet. So we're going from a smaller unit to a bigger unit. So we are going to use division. So we know that 1 foot is equal to 12 inches. So we're just going to divide our 48 inches by 12. So 48 divided by 12 gives us 4 feet, which is the correct answer to problem 2. Our next example is 3 yards to how many feet? So again, we're going from a larger unit to a smaller unit, so we're going to multiply. We know that 1 yard is equal to 3 feet. So we are going to multiply by 3, and that is going to give us our correct answer of 3 yards is equal to 9 feet. So how many inches are in 2 miles? So as we can see up here, we know that 1 mile is equal to 63,360 inches. So 1 mile is equal to 63,360 inches. So we know that we have 2 miles in our example, so we're just going to multiply that 2 by our 63,360, and that is going to give us 1,260,720 inches. So how many feet are in 26.2 miles? So you might recognize this because this is actually what we run when we run a marathon, right? So how many feet are we actually running? So as we know, 1 mile is equal to 5,280 feet. So what we're going to do is we're going from a larger number to a smaller number, so we're going to multiply. So we're going to multiply that 26.2 miles by our 5,280 feet, and that is going to give us a total of 138,336. And lastly, we're going from feet to yards. So we have 900 feet is equal to how many yards? So we know that 1 yard is equal to 3 feet. So now we just need to do our conversion. Remember, we're going from a smaller unit to a bigger unit, right? So we're going to divide. So we're going to divide our 900 feet by 3, and that is going to give us our answer of 900 feet is equal to 300 yards. So next up, we're going to tackle weight when it comes to the standard system. So the number one thing that the TEAS always loves to test you on is pounds to ounces. So as we know, 1 pound is equal to 16 ounces. So this is going to be the key one for you to remember when you're taking that math portion. So our first example says 3 pounds is equal to how many ounces? So as we know, 1 pound is equal to 16. We're going from a larger number to a smaller number, which means we're going to multiply. So we're going to multiply 3 pounds by our 16, and that is going to give us our answer of 48 ounces. Our next example says we have a 5-pound bag of flour, and we need to convert that into ounces. So again, we're going to do the exact same thing as we did in example 1, and we're going to multiply our 5 by 16. 5 times 16 is equal to 80, and that gives us our correct answer of 80 ounces. So for our last 2 problems, we're going from a smaller unit to a larger unit. So when we go from small to large, we actually divide. So in this case, we're going to divide each one by 16 in order to get our answer from ounces to pounds. So our first one is 64 ounces is equal to how many pounds? Well, 64 divided by 16 is equal to 4. And our last one, 96 ounces, is how many pounds? Again, 96 divided by 16 gives us 6. So for each answer, we know 64 ounces is equal to 4 pounds, and 96 ounces is equal to 6 pounds. Let's explore a mnemonic to recall the U.S. customary units used for measuring liquid volume or capacity. I like to refer to this as big G or super G. To start with, we're going to draw a large capital letter G. This is going to symbolize our gallon. This G serves as the foundation for understanding the hierarchy of liquid volume measured when we use U.S. customary systems. Next up, we're going to add 4 Q's inside of our big G, symbolizing that gallons equals 4 quarts. For each quart represented by Q, we're going to introduce 2 P's, indicating that each quart is going to consist of 2 pints. And lastly, each pint is comprised of 2 cups. So we're just going to put our little C's inside of our big P's to represent that we know that there's 2 cups in each pint. This means that 1 gallon is equal to 4 quarts, is equal to 8 pints, and is equal to 16 cups. That is the easiest way that you're going to remember how to break down liquid volume when you're taking the TEAS. Another important concept that doesn't quite fit inside of this is tablespoons to teaspoons. So this one you're just going to have to memorize a little bit. But as we know, 1 tablespoon is equal to 3 teaspoons. So let's do some practice questions to figure out how we're going to solve these capacity problems. All right, let's start our conversions. So as we know, our first question says 3 gallons to how many quarts? So we know that 1 gallon is equal to 4 quarts. So we're going from a larger number to a smaller number. We're going to multiply. So we're going to multiply our 3 gallons by 4, and that is going to give us our correct answer of 12 quarts. Our next question says 8 cups is equal to how many pints? So as we know, Between cups and pints, we have, for every 8 pints, we have 16 cups. So that's basically, just to make it a little bit easier, is 2 cups per 1 pint. So what are we going to do whenever we're going from a smaller number to a larger number? We're going to divide, right? So we're going to divide our 8 cups by 2, and that is going to give us our correct answer of 4 pints. So how many teaspoons are in 4 tablespoons? So as we know, 1 tablespoon is equal to 3 teaspoons. So again, we're going from a larger number to a smaller number. We are going to multiply. So we are going to multiply our 4 tablespoons by 3, and that is going to give us our correct answer of 4 tablespoons is equal to 12 teaspoons. And then lastly, we have 5 pints is equal to how many cups? So as we talked about before in example 2, we know that 1 pint is equal to 2 cups. So what are we going to do when we go from a larger number to a smaller number? We're going to multiply. So we are going to multiply our 5 pints by 2, and that is going to give us our correct answer of 10 cups. So I put a little cheat sheet up here on your screen because these are the most common conversions that you're going to see when it comes to the standard measurements of length, weight, and capacity. So just become very accustomed to these. Sometimes the TEAS is actually going to give you the formula, sometimes they won't. So it's good for you to have a general understanding of how to calculate between them in case you encounter these questions on the TEAS. Let's talk about my favorite system, the metric system. Metric conversions are going to be key for you to understand when it comes not only to the ATI TEAS, but also healthcare in general. And the mnemonic that I want you to use to remember this is, King Henry doesn't usually drink cold milk. By using this phrase, it's going to help you remember the order of metric prefixes when it comes to kilo all the way to milli, relative to the unit base, which could be grams, meters, and liters. So at the heart of our mnemonic, we symbolize the word usually with units. This is where your general units are going to lie, whether you are doing grams, liters, or meters. And around this core are prefixes that indicate whether we're dealing with units that are larger or smaller than our base unit. So as we move to the right towards cold milk, we're going to encounter smaller units, deci, centi, milli, each representing a factor of 10 smaller than our base. Conversely, as we move leftward from our units, we're going to encounter the higher numbers, our King Henrys, right? Our deca, hecto, and our kilo, each representing a 10-fold increase over our base unit. So a kilo therefore signifies a quantity of 1,000 times larger than our base unit. So this framework is going to categorize and quantify the relationships between different metric units. Just like we did in our decimal placeholders video. By the way, if you haven't done so already, make sure you go back and watch that to understand what we're about to do right now. We're going to move the decimal either left or right, depending on the value that we are converting from. So here's a couple of examples to help us with this concept. So we start with our first example, which is 2,500 milliliters to kilometers. So how do we do this? So what we're going to do is we're going to move our decimal place. So it's kind of not really given here, but we can just assume that the decimal place is right after our whole number, which is 2,500. So what do? We know we're going from millimeters to kilometers, right? So we're going to move our decimal place 1, 2, 3, 4, 5, 6 times to the left. So that's ultimately going to give us the correct answer of 0.0025. Because if we did this, just so that everybody can see, here's our decimal. We're going 1, 2, 3, 4, 5, 6. Decimal goes here. We add our zeros where we didn't have them before, and that gives us our correct answer. Our next question, we're going from liters to kiloliters. So again, here's our base unit where we find liters, and we're going to move our decimal place 1, 2, 3 times to the left. So I'm going to write my number out here at the bottom. Our decimal place is right here. We're going to go 1, 2, 3 times to the left. So as we know, 750,000 liters is equal to 750 kiloliters. So in our next question, we're going in the opposite direction. So we're going from kilometers to centimeters. So we are moving from here all the way down here. So we're going to move our decimal to the right 1, 2, 3, 4, 5 times. So writing out our number, 42.195, we're going to move it to the right 1, 2, 3, 4, 5 times. And that is going to give us our correct answer of 4,200,000 219,500 centimeters. Now for our last example, we're going back the other way. So we're going from milligrams to kilograms. So we're going to move our decimal 1, 2, 3, 4, 5, 6. So writing out our number 250 milligrams, we're going to the left 1, 2, 3, 4, 5, 6. We're going to add our zeros that we didn't have before, and that is going to give us our correct answer of 0.00025 kilograms. So metric conversions really are quite simple when you think about it. It's just moving the decimal place either left to right. But now we've got to figure out how we're going to convert between the two systems. That is one of the most commonly missed types of questions that we see on the TEAS, is taking measurements from the standard system and converting them to the metric system. So over here on the right side of your screen, again, I gave you a little cheat sheet of the most common ones that you're going to see on the ATI TEAS. These are the good ones to remember in order to pass these types of questions. So our first question is 50 pounds is equal to how many kilograms? So this is going to be huge when it comes to healthcare because we are constantly converting between pounds and kilograms. So make sure you commit this one to memory. So 1 kilogram is actually equal to 2.2 pounds. So we're going from pounds to kilograms. We're going to divide by 2.2, and that is going to give us our correct answer of 22.73 kilograms. Next up, we're moving from inches to centimeters. So as we know, 1 inch is equal to 2.54 centimeters. So again, we want to multiply this time, right? We're going from inches to centimeters. So 20 times 2.54 is going to give us our correct answer of 50.8 centimeters. Our next conversion is 5 miles to kilometers. So 1 mile is actually equal to 1.6 kilometers. So we're going from miles to kilometers, so we're going to multiply, and we're going to multiply by 1.6, which is going to give us our correct answer of 5 miles is equal to 8 kilometers. So how many meters is in 30 feet? So 1 meter is equal to 3.28 feet. So again, we're going from feet to meters, so we're going to divide. We're going to divide by a 3.28, and that is going to give us our correct answer of 9.15 meters. And our last question is 100 grams is equal to how many ounces? So 1 ounce is equal to 28.35 grams. So again, we're going from grams to ounces. We're going to divide. We're going to divide by 28.35, and that is going to give us our correct answer of 3.53 ounces. Whew, that was a lot. That's everything you're going to need to know in order to ace that math portion of the exam. If you have any questions, make sure that you leave them down below. I love answering your questions. Head over to nursecheungstory.com where there is a ton of additional resources available to you. And as always, I'll catch you in the next video. Bye!